କାଲି ରାତିରେ କହିଥିଲି ସକାଳୁ ମନେ ପକେଇବୁ ନା।
Hello, good morning everyone. Good morning, sir.
Good morning.
How are you, sir?
Yeah, I am fine. So can you check my screen is visible?
Yes, sir. Yes, sir. It's visible.
Okay. Okay, at the top I will make it full screen.
Okay. Assalamu alaikum, Afroz sahab.
जी वालेकुम सलाम। आवाज आ रही है मेरी?
Yeah. Dr. Afroz will chair this session, and this talk is of Professor P.K. Sahu from BITS Pilani. So over to you, Afroz sahab.
Okay. Thank you very much, Majid Saab. Welcome once again for this morning session, all of you. In this session, Professor P.K. Sahu is the speaker of this session. I'm in the meeting. Hello. Hello.
Yeah, Afroz sahab. Please carry on.
Before call to the speaker, I would like to say something about the speaker. Professor P.K. Sahu is professor and head in the Department of Mathematics, BITS, Hyderabad. He has very vast teaching experience, more than 20 years. He has been placed among the top 2% scientists of the world according to the survey by researchers from Stanford University, USA. And this is a very big achievement. And we are lucky that such a renowned speaker is with us today. He is a fellow of Institute of Mathematics and its Applications, London, fellow of Royal Astronomical Society, London, and also many more. Professor Saho has been completed many government funded projects like UGC, CSIR, and BHM, and he has been supervised 10 PhDs and visited many countries like Spain, UK, Japan, Belgium, Germany, South Korea, and many more. And he has been published more than 140 papers in reputed journals. Professor Shaho delivered more than 20 invited talks in national and international conferences, symposium, and organized many conferences. And he is a member of many editorial boards and reviewers of many journals, life member of societies. Now I request Professor Saho that he delivered his talk and graced the audience. Professor Saho.
So thanks, Professor Afroz. Good morning to all. And first of all, my sincere thanks to the organizing committee to giving me the opportunity to speak about my research. And my special thanks to Dr. Majid for inviting me. So let me start the talk. So the title of the talk is Wormholes in Exponential FRT Gravity. So basically in this talk, I will go through the basic introduction. What about the wormholes? Then why we'll study the wormhole and the history of the wormholes. Then in the next session, I will go for this solution of the wormhole geometry in a modified FRT gravity. And we have approached here the exponential FRT gravity. So the solution, the equation of state, the solutions and the energy conditions in the exponential FRT gravity, and the conclusion of the talk. Okay, so let me start from the very basics, the wormhole. Okay, so before going through the wormhole, the first question is, can we travel through wormhole? The time travel through wormhole. Can anybody has any answer for this? Whether it is possible or not? Okay, so so basically this is a theoretical study, and the answer for this is, though it is completely not possible, okay, but we have science fiction. So these are the science fictions which we did here, and these wormholes are mostly used in the Hollywood movies. So if you go for this movie Contact in 1997, so there you can see this Jodie Foster traveled to another planet by the help of a wormhole. After that, in movie Thor in 2011, so this wormhole was used between Earth and Asgard. Then in movie Interstellar, if you go through 2014, so Matthew and Annie, so they used this wormhole to travel to the farthest region of the universe in search of habitable planets. So this is basically the Hollywood's depiction of the wormholes and the interstellar travel. So which continue to the fascinate scientists and the space enthusiasts that exactly what are the wormholes and how do they work. So that is basically, though it is a theoretical study, but its fascination was used in the Hollywood movies. So basically it is a time travel. So one can travel from nearest one galaxy to other galaxy or inside the galaxy also. Then coming to the wormhole history. Okay, so a wormhole basically is a hypothetical shortcut between two distinct regions on the space-time. So yesterday we have many lectures, and we discussed about this space-time geometry. So in the space-time geometry, it is basically to go from one region to other region. We can use the wormholes, and how to visualize it. How will you visualize these wormholes? Okay, so if you go for a two-dimensional space, right? So just I'll go for the image. So see, so just a paper, I folded a paper. Okay, so take a piece of paper and fold it. Then one wants to travel from a point A to point B. So in place of traveling this whole surface, okay, whole surface from A to B, what one can do, one can go make a hole from A to B. So this is the shortcut. So that is the idea of wormhole which was introduced here. Okay, so in two-dimensional space, as a folded piece of paper, if you embed in a higher three-dimensional space, then you can see a tube connects two distance points A and B. So the length of the tube can be much less than the distance from A to B along the paper. So that is what this length A to B, you throw the tube is the shortcut distance. So that is what the basic idea of this wormhole. Right. So if you go for three-dimensional, okay. So just I'll show this. So this is looks like spherical. Then when you go for the three-dimensional, so this is one mouth, and the other end is another mouth. So this is the throat. This is the throat connecting two mouth or the two spherical regions. Fine. So this is what in three-dimensional space. So when you go for a fully three-dimensional wormhole, so it is the entrance and exit. So there are two mouths, as I told. Okay, so they are the three-dimensional spheres. Like, so in place of the two-dimensional mouth. So this is basically the mouth, and the lower dimensional is human friendly. So these visualizations are termed the embedding diagrams. So what I showed here, they are known as the embedding diagrams, and the iconic wormhole image is usually shown as the well-known Schwarzschild embedded diagram. So these are known as the embedding diagrams. Okay, so these are static and non-rotating Schwarzschild black hole metric. Fine. So this is the wormhole in 2 dimension and 3 dimension. Now coming to the Einstein's general relativity. So in Einstein's general theory of relativity, the wormholes are expected to be filled with exotic matter. Then what is this exotic matter? So the exotic matter, that is basically which does not satisfy the energy condition, in particular the null energy condition. So I will discuss the details about the energy conditions. So there are four popular energy conditions. Okay, so out of that, if the violation of non-energy condition leads to presence of the exotic matter. So a wormhole basically known as the Einstein-Rosen bridge, and it is a topological feature that would fundamentally is a shortcut connecting two separate points. So that is already I told, separate points in the space-time or the regions in the space-time. And they contain two mouths and a throat, which already I showed in this spherical embedding diagram, the three-dimensional embedding diagram. So the two ends are called the two mouths, and it is connected by the tunnel. That tunnel is known as the throat. Okay, so the term wormhole, particularly introduced by American theoretical physicist this John Wheeler in 1957. So the term was coined by John Wheeler in 1957, though the study of wormholes are much earlier. Okay, so why the name was given as wormhole? So the idea is, suppose a worm. So if you see this figure, suppose a worm wants to go one end to other end. So this is an apple. So the worm wants to go from one end to other end of the apple. So what the worm will do? So in place of traveling through the skin of the apple, he can make a hole from one end to other end. So that is a shortcut in place of traveling through the skin of the apple. So that is what the idea gave to John Wheeler to name this as a shortcut distance or the wormhole. Right. So if you see these two figures, so the left-hand side figure almost everybody knows that if you take a piece of fabric or simply you take your handkerchief and keep some weight, okay, then the sag towards the center due to the gravitational pull. Okay, and the second one is nothing but the black hole. So when there is heavy gravitational pull, then you will get the black hole. Okay, so the supermassive black holes cause a tear in the space-time, and this tear is called the wormhole. So that is what the second figure. Okay, so these two regions should meet and they form a wormhole connection. Right. So particularly these wormholes are not black holes, because black holes, as we know, it is one-way trip. So anybody can enter towards the black hole, but nothing can exit. But what about wormholes? In wormhole, there is two mouth through the throat, so one can enter and exit. So it is a two-way trip, whereas the black holes are only one-way trip. So this is what I gave the picture. So in black hole, one can enter, but nothing can exit due to the supermassive. But what about wormhole? One can enter and he can exit in the other end. Right. So then the next question is, do these wormholes really exist? So what is the answer for this? So do the wormhole really exist? So as I mentioned from the beginning, there was no experimental study, or there is no proof that the wormholes exist. It is only a theoretical study. Okay. So there is no observational evidence for wormholes currently exist, but the mathematical solutions which describing wormholes have long been known as the valid theoretical solution. So these are the theoretical solutions to the Einstein field equation in general theory of relativity. So as I mentioned, that the violation of non-energy condition leads to the presence of exotic matter, which is a minimum requirement for the existence of the wormholes. Okay, so these wormholes made completely normal matter with positive energy density, and they are inherently unstable, and they will collapse very fast in the presence of nearby matter, or matter that try to traverse through the wormhole. So for going these traversable wormholes, which was used mostly in the Hollywood movies. Okay, so these stable traversable wormholes could exist if their entrance and exits were open by the exotic matter. And sometimes you will get the negative energy density also, because if you study the Kashmir effect, so there you can get this negative energy density. Right. So coming to the history, as I mentioned, though John Wheeler coined the name wormhole in 1957, the study of wormholes are much before that. So it was, so as all of us knows that Albert Einstein started the general theory of relativity in 1916. Then Flamm got the Whitehall solution in 1916. After that, Schwarzschild. Okay. So Schwarzschild got the Schwarzschild solutions, which is well known and all of us knows that he got the first exact solution to the Einstein field equation, and that is known as the spherical symmetric vacuum solution. So that is basically one image. Then 1921, Weyl first proposed the wormhole theory. So wormhole theory was proposed by Weyl in 1921. Then the most prominent was in 1935, the Einstein-Rosen bridge, which was studied by Albert Einstein and Nathan Rosen. So this is the book, actually, the cover page of the book. A wormhole is a theoretical passage through space-time. Then after 1935, then Gödel proved that there is a time tunnel. There is a tube through to both the ends. It was given by Gödel in 1948. Then Wheeler coined the name as wormhole in 1957, and the most prominent was Morris and Thorne. And all of us knows that Kip Thorne got the Nobel Prize in 2017, but not for wormholes, he got for these gravitational waves. But if you go through the Hollywood movies, what was used the wormhole, that was the Morris Thorne wormhole. That is the most popular, known as the traversable wormholes. So the traversable wormholes are used, and in the movie Interstellar, they have taken the help of Keith Rooney. Okay, now coming to the type of wormholes. So that what I told, that is the background of the wormholes, the history. Now coming to the various type of wormholes. So as we know, if you go for the mathematics, so when we are going for a particularly differential equation, we are classifying the differential equation based upon their nature and all. So somebody is telling that it is ordinary differential equation, partial differential equation. People are telling that it is linear differential equation, nonlinear differential equation. So based upon their nature and the behavior, we used to give the names. Okay, so similarly, there are many type of wormholes. So many wormholes are named after the physicist or the scientist, those who discovered it. So same thing as the Schwarzschild wormhole, Lorentz wormhole, Maurice Thorne wormhole, Ellis wormhole, then Matt Visser also, so Visser wormhole. So these are the named wormholes by the physicist. After that, there are different 6 type of, particularly there are primarily 6 type of wormholes, which are all the scientists are agreed. So what are these 6 type of wormholes? So first one is the traversable wormhole, which I told was developed by Maurice and Thorne. And these are the wormholes, so we can pass through from one point to other point in the universe. Then the non-traversable, so nothing can pass through, either because of the wormhole collapse, like white holes. But the particular example is white holes, which are less massive and they diffuse very quickly. So there is always a question between what is wormhole and white hole. Okay, so it has only one entry point, but there is no existence, or the region, the person or the particle entering it would be destroyed before reaching the other side, because it will diffuse very quickly due to less mass. Then another one is known as the one-way wormhole, that is particularly the black holes. So wormholes are one-way trip, meaning you can only travel once through them, and you would need to a separate wormhole for the return trip. The example is black hole, that is what I mentioned here. Then coming to the white holes, already I mentioned that due to less massive, then nothing can enter in the white hole, because due to less massive, it will collapse very fastly. Now coming to the two-way, so the two-way wormholes are the round trip. Okay, so one can enter from one end and exit in the other end. Then the intra-universe. So what are the intra-universe wormholes? So particularly the intra-universe wormholes are located in our own universe. So you can travel from one point to the other point in the own universe. Then inter-universe wormholes from one universe to the nearest galaxy, nearest universe. So from one parallel universe. In a parallel universe, one can travel from one to other. So that are the inter-universe wormholes. Okay, so this is basically a artistic diagram how the wormhole is going through it. Okay, right. So the basic idea is we want to create a traversable and a stable wormhole for use in the space travel. So the idea, basically the ideal type of wormhole for travel, and the one we see is the most often in science fiction is the intra-universe. So in science fiction or the Hollywood movies, particularly the intra-universe, that is the two-way traversable wormholes are used. So this wormhole would allow a traveler to make a journey. Okay, so within our universe or from one universe to other universe.
आज क्लास नहीं होगी हम उसमें इस कॉन्फ्रेंस में.
Okay, so this is basically a diagram which I made that Einstein from Earth to the nearest galaxy.
आज कुछ नहीं होगा, प्रोग्राम चल रहा है.
Galaxy is the Andromeda galaxy.
अटेंडेंस अलबत्ता दे देना.
So this is what wormhole Einstein is traveling from one galaxy to other galaxy. Right. Now let us come to the mathematical part. Right. So just I went through the basics, what is wormhole, how it started, and why we study the wormhole and different types of wormholes. Now I will enter to the mathematics part. So as all of us know, when you go for a cosmological model, you basically will start with the space-time. So particularly if you go for cosmological models, we go for the Friedman-Robertson Walker metric, FLRW metric. So similarly, here the wormhole has the Schwarzschild coordinates with static spherically symmetric metric. which is given in equation 1. So if you go for equation 1, this r theta phi, you know the spatial coordinates, and t is the time coordinate. So here there are two unknowns. One is phi, another is b. So this phi and b both are functions of the radial coordinate r. One is known as the redshift function and another one is known as the shape function. So particularly the distance or the travel we can measure through the space function. Okay, so that is basically the b of r. The shape function measures, like if you go for the FRW metric, so the expansion we use to measure through the scale factor. So a of t, the scale factor measures the expansion or the acceleration. Similarly, the shape function here measures the traversable. So what about the throat distance and what is the all this geometry will be discussed through the shape function. And as we are familiar, or the most prominent are the traversable wormholes. For a traversable wormhole, the redshift function phi of r must be constant. Okay, so here this r, the radial coordinate, is from r0 to infinity. Then what is r0? R0 is known as the throat radius, because as I am told, there are two mouths and a throat is connected to the mouths. Fine. Now, when you go through the wormhole geometry, to study the wormhole geometry mathematically, we need 4 basic conditions. So the wormhole metric must satisfy 4 minimum requirements. So what are that requirements? The first condition is at the throat, r, that is r is equal to r0. So b of r0 is equal to r0. So this is known as the throat condition. The first condition is known as throat condition, which is given in equation 2. Then the second condition is known as the flare out condition. So in the flare out condition, the first derivative of the shape function with respect to r at the point r0 must be less than 1. Then the third condition is known as the asymptotically flatness condition. So throat condition, flare out condition, then flatness condition. So the third one is given in equation 4. For the space-time geometry, the limit br by r must tends to 0 when r increases to infinity. And for a traversable wormhole, as I mentioned, the redshift function must be constant. It is finite everywhere. So these are the 4 minimum requirements for a traversable wormhole. Right. Now coming to the exotic matter. So it is different from the dark matter. Don't confuse with the exotic matter and dark matter. Okay. So exotic matter is basically the matter where the null energy condition violates. And in case of this quartzite wormhole, it was found that it would collapse too quickly for anything to cross from one end to the other end. Fine. And as I mentioned, for a traversable wormhole, so only be positive if exotic matter with negative energy density could be used to stabilize it. Right. So for the development of wormhole structure, an exotic fluid is required which violates the null energy condition in general theory of relativity. So this violation of energy condition is regarded as one of the basic requirements for wormhole construction. Okay. Now coming to the energy conditions. So energy conditions are nothing but the Raychaudhuri equations. Okay, so Professor Amal Kumar Raychaudhuri from Presidency University, okay, earlier it is Presidency College, who gave the equations to know whether the space-time is time-like, space-like, or light-like course, right? So it is commonly known as the GR to establish and study the singularity. So if you go for the Penrose equations or Hawkins equations, all of them use these Raychaudhuri equations to get the singularities. Okay, so already I told there are popularly 4 types of energy conditions. So the first one is the null energy condition. So the null energy condition says that the density plus pressure must be greater than equal to 0, which is given in equation 5. Then coming to the weak energy condition. So the weak energy condition is a addition to the null energy condition, that the density is always positive with null energy condition. Okay, so it says that the effective energy density should be always non-negative when it is measured by any observer. Right. So by continuity, if weak energy condition satisfied, then it implies that null energy condition must satisfy. Then the strong energy condition, which is mostly used in cosmology, because the violation of strong energy condition leads to accelerated expansion. Okay, so it says that the gravity should always be attractive. Okay, so in terms of our special energy tensor, the sum of the rho plus all the pressure, because here we will get the radial pressure and tangential pressure. So sum of this radial pressure, tangential pressure, and the density must be positive. Right. Then the fourth one is the dominant energy condition. The dominant energy condition says that the density dominates the pressure. So the density is greater than or equal to magnitude of the pressure. So the effective energy density must always be positive when measured by any observer. Okay. So these are the four types of popularly known as energy conditions. Now coming to the wormhole solution in FRT gravity. So as I mentioned from the beginning that I will use a modified gravity. Okay, so here I use the modified gravity known as the FRT gravity. So it is a coupling between geometry and matter. So if you see this F of RT, so R is the Rishi scalar, which describes the geometry of the space-time, and T is the trace of the energy momentum tensor. That is nothing but your matter present in the universe. So it is a coupling between geometry and matter, right? So every theory has Einstein-Hilbert action. So we start with the Einstein-Hilbert action of the FRT gravity, which is given in equation 9. Okay, so already I told what is R and T, and L is nothing but the matter Lagrangian, which may be pressure or density, and you know G is the determinant of the metric potential, Gij or G mu nu. Right. So here we have considered this anisotropic fluid of the matter in the form of equation 10, where rho is the density, Pt is the tangential pressure, and P are the radial pressure. And Ui, Uj, you know these are the four velocity terms, and Xi, Xj are the radial unit 4 vector. Right? So Ui is the 4 velocity vector and X is the radial unit vector, and they satisfy this condition. Right. So to construct the general field equations for this wormhole metric in FRT gravity, what we have considered. So we have taken a functional form of FRT R plus gamma e to the power chi t. So we have considered an exponential form of the trace of energy momentum tensor. So the T has an exponential form. That's why I gave the name as exponential FRT gravity. And this was proposed by us. Okay, so this exponential gravity is proposed by me and my collaborator, which is published in European Physical Journal C in 2019. Okay, so taking this form of the FRT gravity, we get the field equations which are given from 11 to 13. So if you see 11 to 13, okay, 11 to 13, there are three field equations having four unknowns. Okay, the density, rho, then radial pressure, tangential pressure, and the shape function. So we have a system of three equations with four unknowns. Fine. So which is a underdetermined system. To get an exact solution for this underdetermined system, we need an additional condition. Okay. So what we did here, to find the solution, since it is underdetermined, we have considered the additional condition as the equation of state parameter. As all of us knows, the equation of state parameter is nothing but the relation between the pressure and density. So the density can be written as a function of pressure. So the same thing we have used here. To get the solution, we have used the equation of state, which is given in equation 14 and 15. Okay. So the radial pressure is alpha times rho, and the tangential pressure is beta times rho. So this alpha and beta are the equation of state parameters, which are the constants. So taking this equation of state, we wrote the density in equation 16 from the field equations. Okay. So here just I replace this alpha plus 2 beta by xi. Okay. And this W. So the W is the Lambert's function, or which is known as the product logarithm. Yeah, we'll take the questions once I finish. Right. So coming to the model. So what we did, we went for the solution of these field equations. So in the first model, we have considered a power law form of the shape function. So considering the power law form of the shape function, we got the density which is given in this equation. And then in the power law model, okay, so we checked the three conditions: the throat condition, flatness condition, and the flaring out condition, whether the three conditions are satisfied or not. So we have checked these three conditions which are plotted in this figure. So the behavior of the shape function, okay, with the R0, the throat radius is 1 and the free parameter M is 0.5. Right. Then coming to the material solution and the energy conditions. So for the model A, the equation of state parameter with alpha is equal to 1/3 and beta is equal to 1, we plotted the three energy conditions and the density. Okay, so this is the density. You can see the density is positive. Then here you can see all the energy condition. This rho plus PT, rho minus PT, rho plus PT plus PR plus 2 PT. Okay, so this is the strong energy condition. Then this one is the null energy condition, and this is the dominant energy condition. Okay, so the null energy condition, dominant energy condition, and strong energy condition, if you see, all are validated here. Okay, so the matter energy density of the wormhole constructed in the present formalism, as well as its energy condition in terms of the function R, as in this figure, and one can observe that all the energy conditions are validated here. Now, okay, I'll come to your question. Let me finish this talk. Okay, so coming to the solutions for the energy conditions with alpha is equal to 1 and beta is 1/2. So if you go for here, so here we have taken alpha is 1/3 and beta is 1. So with the values of the equation of state parameter, we can observe that all energy conditions are satisfied. Now coming to the second model, okay, when alpha is equal to 1 and beta is equal to 1/2. So here also you can observe that all the energy conditions are satisfied. Okay, the energy density, this is the null energy condition, this is the dominant energy condition, and the strong energy condition. So the behavior of the matter energy density and the energy conditions in terms of R in the present formalism of the wormhole model B are presented here, and all are validated. Right. So coming to the conclusion of the talk or the summary. So this particularly the wormholes are tube-like structures, okay, which are known as the shortcuts connecting two distant regions in the universe. Or if you take the space-time, then two regions or 2 points in the space-time. So their geometrical structure was not singular enough. So according to this general theory of relativity, so wormholes are expected to be filled with exotic matter. That is basically the negative mass. Then the lack of observations of wormholes makes one unable to predict exactly some of their geometrical and material properties, such as the shape function and the equation of state parameter. Okay, so in this present talk, so we have considered a functional form of the FRT gravity as R plus gamma e power chi t, where gamma and chi are the model parameters. Okay, so before going for any other discussion, so we would like to mention that the power law shape function, which is in equation 17, and satisfied all the requirements needed for a traversable wormhole. And we have presumed the relations of the equation of state parameter inside the wormhole. So further, we have considered two models, model A and B, with different values of the model parameters, the equation of state parameters alpha and beta. Okay, and we checked that for both the models, the energy conditions are satisfied. Okay, so for exponential gravity, it is possible to obtain wormhole solution, and they satisfy all the energy conditions which are given in figures 2 and 3. So those figures were plotted for different cases of equation of state PR is equal to alpha times rho and PT is equal to beta times rho. So this shows that the respectively the energy conditions weakly depend upon the equation of state parameter. Okay, so to conclude, these are the minimum requirements of the shape function, which is plotted in figure 1, and they satisfied. So these are some references which I used in this talk. So thank you for your patience. Okay, let me go for the messages. What is the question? Okay, so what is the physical significance of FRT gravity in symmetries or space-time manifold? So particularly if you go for FRT gravity, right? So just I will start why there is a need of FRT gravity, right? So if you go for Einstein's theory of relativity, so in Einstein's theory of relativity, though it is a well-tested gravity, so it fails to explain the flatness problem and some singularity issues. Okay, so even if the event horizon, in the horizon also, so there are some lacuna in Einstein's theory of relativity which is not able to address all the queries. So that's why from time to time people modified the general theory of relativity with its matter content or the geometrical changes. So as all of us knows that the Einstein field equation, the left hand side tells about the geometry and the right hand side tells about the physics. Okay, that is because the right hand side contains the matter. So there is a modification for the matter or there is a modification of the geometry to get a new gravity, right? So the more well known gravities are the FR gravity, FT gravity, and so on. Okay, so FR gravity, if you go for FR gravity, the modification of the Rishi scalar R, which is the nothing but the curvature of the space time, right? So if you go for teleparallel gravities, so they are the then the torsion gravity, so they are the modified the physical part. So similarly in this theory F of RT, it is a coupling. It is a coupling between the matter and geometry, right? So both the matter and geometry are coupled with this gravity. As in Einstein's field equation, so what it says, the matter and geometry. So geometry rules the matter. If you go for Einstein's theory of relativity, the geometry which rules the world and the world which is ruled by this geometry. So here what we did, we changed this action of Einstein's theory of relativity using the coupling of R and T. Okay, so it changes the coupling, that is basically matter and geometry, the Rishi scalar, so the curvature and the matter. So that is what the changes in this modified gravity. And in space-time, what you mentioned, the space-time manifold, particularly the change of the curvature was introduced in this theory through this Rishi curvature scalar or the Rishi scalar. Okay, any other question?
I think there is no question now, and even nothing in the chat box. So thank you very much, Professor Shaho. Such a nice lecture. Thank you very much.
Thank you, sir. Thank you for your opportunity to speak about my work. Thank you a lot. Thanks a lot.
Now our next speaker is Ben Jilali Gerici. He is Associate Professor in the Department of Mathematics, University of Mascara, Algeria. He has been working in differential geometry, Riemannian geometry, structure of manifolds, and symmetry properties. So, and he has been published many research papers and delivered many invited talks. So I request Ben Jilali that he delivered his talk. Hello, are you there, sir?
He was there in the meeting. I've seen him.
But right now he's here.
Professor Beldi Ali, are you there?
Professor Bal Jilali.
Hello, are you there, sir?
He's in the meeting.
Somebody's Buhari Haruna. Is this you, sir?
Someone speaker is unmute.
Yeah, I'm muted.
And his baby is crying or playing. So it's coming here.
So I'm trying to connect with Professor Beldi Ali. Please have patience for 5 minutes. Really sorry, and I apologize on behalf of organizers for this glitch. And we are trying to connect him. Just hold for 5 minutes.
Hello.
Hello. Okay.
Yes, Dr. Majid.
Yes, sir. Sir, just
Yes,
have a second.
just I am sharing the PowerPoint.
Okay, sir. You can, sir.
Now, can you see is it visible? Can you see the slide?
Sir, it's visible, sir. It's visible.
Okay.
Sir.
Okay. Just myself, my Muhammad Nazrul Islam, and I am giving to thanks to organizing committee.
Sir, Dr. Najul Islam, sir. Dr.
Okay,
Afroz, Dr. Afroz is the chair. He will introduce you. Just
okay.
have a second.
Sorry, sir. Okay, no problem.
Now our Dr. Muhammad Khan, he received MSc and PhD degrees from the University of Lucknow in 1997, and currently he is working as assistant professor, College of Computer, Karachi, Saudi Arabia from 2011. Before joining Karachi University, he joined Al College of the Oman in 2009 as a lecturer. Joined the Azad Institute of Engineering and Technology, Lucknow in 2000 and become assistant professor in 2003. He has served as the head of the Department of Applied Sciences and Humanities, Azad Institute of Engineering and Technology from 2008 to 2009. Dr. Khan has written 2 books and published more than 50 research papers in various journals of national and international repute. Now I request Dr. Muhammad Nazrul Islam that he delivered his talk.
Okay, thanks, Professor Atif. And I am giving to thanks to Dr. Majid and organizing committee to give me chance to present the paper here. So my talk title is Metallic Structure on Differentiable Manifold to Frame Bundle. First, I will discuss about what is the frame bundle and then about the metallic structure. After that, I will introduce the metallic structure in the frame bundle and different diagonal lift, horizontal lift and complete lift. I operate on the Riemannian metric and we found the following results. The derivative and co-derivative of the form Nijenhuis tensor and metallic Riemannian metric of the newly defined tensor. First, I will brief discussion about the frame bundle. Suppose we have any C infinite, be the algebra of the C infinite function in the Euclidean space, whose coordinate are x1, x2, xp, and there are 2 functions, f and g, be the 2 elements of this C infinite. And also suppose that f be an n-dimensional manifold. And we consider that u and b the 2 neighborhood at the point x equals 0. So we have the mapping. Suppose f mapping from u to m is the manifold, n-dimensional differentiable manifold, and V is also another subspace. Then M is the manifold. Then we have 2 mapping F and G. Then we define a 1Z if these satisfies these 2 conditions. F0 equal F0, G0 and del by del X F and del by del X G satisfies, then it is called 1Z. After that, we consider this mapping, all of mapping phi. Suppose this is a mapping of phi from Rp to M. This is the set of the all mapping. So we consider 2 mapping phi and psi. Then phi is said to be the equivalent to phi if F composition phi is equivalent to F composition psi in for every element of C infinite. Then we again get the equivalence relation and we denote this by Ji phi. This is the equivalence class of phi which belongs to the SPM is the set. Is said to be 1Z in the M. So now we consider let J1PM denote the set of all equivalence classes in XPM, this one, and also we consider phi pi J1 PM tends to this mapping pi from J M to M. This is the projection map and given by this way. This defined in Cardero et al. 89. So when we have this one, this mapping, pi J1 P M to M, this is a mapping. So there are two cases. There are particular two cases. The case one here, two particular values of P. P equal 1, if we consider P equal 1 and P equal n, there are n-dimensional manifold, P1 and Pn. Then it have the two special situation. The case one, when P equal 1, then we have pi J11 M. This is called the tangent bundle of M. Suppose any manifold M, then we here define this map pi J11 M to M is called the tangent bundle of M. And it is denoted by MTM such that TM to M, pi M such that TM to M. This is called the tangent bundle. So first we discussed about the tangent bundle. This is a special case of the frame bundle. So now the theory of the lift, like vertical, complete, horizontal, of any geometrical structure, for example, structure, almost contact structure, almost product structure, metallic structure, whatever the structure, F structure, and connection from the manifold to its manifold was developed by the Yano and Sahara 1973. This is the beginning of the tangent bundle. Now in 2017 and 2018, myself studied the tangent bundle Indo with the respect to semi-symmetric connection in the connection on the Kahler manifold and tangent bundle of the almost Hermitian manifold also and almost Kahler manifold with respect to quarter symmetric non-metric connection. That means we define in 2016 and 2020 on a tangent bundle on the connection. So most recent my paper completely the semi-symmetric P connection to its tangent bundle and the lifting of the metallic structure to the tangent bundles of order R, studied by myself and Dr. Professor Day recently. So this is about the tangent bundle. Actually, tangent bundle is the particular case of the frame bundle. If P equal 1, it become tangent bundle. If P equal n, then this map pi J1PM tends to M is precisely the frame bundle of M and denoted by Fm. This frame bundle denoted by M. So there are in this mapping, there are two cases. If P equal 1, tangent bundle, P equal n is the, if dimension and same, then it become frame bundle. So Cardero et al. 1989 studied the horizontal lift and diagonal lift of the connection and tensor field connection, like semi-symmetric connection, quarter symmetric connection, whatever the connection they studied, and tensor field of the different type of the tensor field. For example, tensor field of 1, 1, tensor field of 0, 2, like this. And they discussed Hermitian structure, Kahler form, and the Nijen-Hayes tensor of the almost contact structure on the frame bundle. This is studied in 89. After that, the curvature of the diagonal lift from an affine manifold to the linear frame bundle were investigated by the Kawasaki and Sekizawa in 2012. Before this, Leon 86, now there are numerous of the geometers studied about this structure on the manifold on the frame bundle for Leon 1986, Nizia Losky in 2015, Lechis Ray in 2020 have studied various geometric structure, for example, almost contact structure, almost complex structure, and like F structure, F cube plus F equals 0. These structure studied on the frame bundle and gave their theories. Most recently, myself, 2021 and 2022 have studied the frame bundle with the metallic structure on an almost contact metric manifold and integrability of the metallic structures on the frame bundle recently published. So now, so suppose we have the let M be n dimensional differential manifold and Fm its frame bundle. So pi is Fm to F is the projection map just I discussed before. So if we have base space M is covered by the any neighborhood of this one uxi such that Fu equals this, then we have a local coordinate xi is defined as in the neighborhood of U. So here we consider a vector xi in the local component defined in the frame bundle like this: x alpha equal xi alpha del x by del xi, x is the suffix as this. So this is called the coordinate system in frame bundle. Fu, xi and capital Xi alpha. This is the coordinate system in Fi. So here we discuss then f x be the tensor field of type 1, f is a tensor field of type 1 1 and vector, and x is a vector field. So fh, xh and alpha, this fh is called the horizontal lift of f, this is horizontal lift of x, and this is the alpha vertical lift of x respectively on the Fm. This alpha lift, x alpha, this is known as alpha vertical lift. If alpha equal 1 in the case of tangent bundle, alpha equal 1, then it is called simply vertical lift. So it denoted by xv, x power v like this fh, and this denoted by xv in the case of tangent bundle. So alpha equal 1 is called one vertical lift, that means vertical lift, and in the case of tangent bundle we take x power v on Tm. This is the Tm. But here we discuss about the frame bundle, so x alpha equal Fm. So here the x power h, the horizontal lift of the x defined in the component form, local component form xi is this one, and x alpha is given this. F and h is tensor field of type 1 1 defined by this one. Okay. So this is the local component. And here suppose f and t be the function and one form, and we also defined by this way. And this is the local component of this given t v upon th alpha th, this given already. This is local component of this is the written in the term of local component. So some property here we will use later. Horizontal and vertical lift are given by this way. This is the Lie bracket also defined here. Lie bracket of the x power alpha and y beta in the frame bundle defined here. Xh, xy alpha like this. This one now here this is the frame bundle. So this is about the frame bundle. Now so we have seen the frame bundle pi is mapping pi FM to M. This is called the frame bundle. And the FM frame bundle, if we consider P equal 1, they become tangent bundle. Now here we discuss the metallic structure about the polynomial. Suppose here given in 1970, Goldenberg and Yanu introduced the polynomial structure like this. Qj, j power nth n degree, polynomial of degree n introduced by the Goldenberg and Yanu, where j is the tensor field of type 1, this, and the differentiable manifold M. Now we consider here the polynomial structure of degree 2. So this means j square equal pj plus q equal I, where p and q are real numbers. When real numbers, so we consider here j square equal pj plus q. This is a polynomial structure of degree 2, or you can say the quadratic equation of degree, quadratic equation actually. So Gonal et al. In 19 this study. So there are, in this case, there are different value of p and q. Different value of p and q, we get the different well-known structures. So there are in particular cases, these structure reduces to well-known structure 1. If p equal 0 and q equal 1, then it become almost product or almost para contact structure, which is obtained. So in 1983, Navera and Pittis 1986 is discussed about this structure, almost product and almost para contact complex structure. If p equals 0 and q equal -1, then it become almost complex structure is obtained. Then almost complex structure is obtained. Yano and Kahn 1984 and Boname et al. In 1986. They discuss this geometric structure, the following properties like curvature and Eisenhower tensor, co-derivative, differential form, the whatever this is the property they studied. And if p and q equal 1 in the above equation, in this equation p and q equal 1, then we get the golden structure. We get the golden, and then Azkan in 14 and Bilen at 19 discuss about the golden structure in the form of some structure like Eisenhower tensor and covariant derivative, like this many properties they discuss. Similarly, silver structure studied by Azkan in 2016. Okay. Now our case here, if p and q are positive integer, if p and q positive integer, then this structure j square plus pj plus q becomes metallic structure. If p and q are natural number, are positive integer, or natural number 1, 2, 3, 4, so then it become metallic structure. Then Professor Braga and in 2018 and 2019 studied this property, and Chaudhary and Braga also studied in 2020. This is Majid Chaudhary. This is the Majid Chaudhary already studied this one. Okay, this is the metallic structure. About the metallic structure, we take the positive value p and q, this become metallic structure. So metallic structure actually originated by the Spinadel in 1999. This is there are many member of the family members like silver, golden, spattle, bronze, etc. Therefore, this is the member of the metallic means family. Now we suppose we consider how we generate this. The general quadratic equation x square minus px minus q equals 0. Then p and q are positive integer. Then we take only positive solution. So you know the quadratic equation minus b plus minus b square under root b square minus 4ac. We get from this, and we get only positive value. So this is called the metallic means family, this one. So here we study the polynomial structure of degree 2, j square equal pj plus qi, where p and q positive is referred as metallic structure on the differentiable manifold in our proposed contest. We take this one. So here, some metallic here, if G be the Riemannian manifold and satisfy this condition, so this one G, P, G, X, J, Y, and P, here this is Q, sorry, this is Q, G, X, Y, then it become the metallic Riemannian manifold. And the Eisenhower tensor also here defined. Now we discuss about the almost contact metric manifold. The Blair 1976 introduced the geometry of almost contact structure and interpreted the geometric property of such structures. Suppose this is a 2n plus 1 dimensional differentiable manifold and consider the tensor field phi, vector xi, and eta is the one form. So this structure is called almost contact manifold. This is a structure. This structure is called almost contact structure, and this manifold is called almost contact manifold. If G involved, metal G involved, it is called contact metric manifold. With this structure is called the metric manifold, almost contact metric manifold. This structure. Similarly, we have the fundamental two form, this one. Now, here. Now, my proposed theorem for the metallic structure on the frame bundle. Actually, in 1986, Boname established defined a tensor field like this. This is the defined. No. From Boname et al., the tensor. Now we define a new tensor here, J curl of type 1,1 on the frame bundle in the metallic structure. This is a metallic structure, J square in this, where P and Q are positive integer. So we introduce, or I introduce this one, J curl equal P upon 2 I minus 2 sigma P and Q minus P and phi H and sigma. This one, now we define this curve, this tensor, we introduce this one in the term of metallic structure. So when I introduce this tensor, then we have to show that this is metallic first, and so we have one theorem here. Let M be a differentiable manifold endowed with the almost contact structure. Then J defined in 17. This J, this J defined in the 17 is a metallic structure on the frame bundle FM. So now we have to show that our defined tensor is a metallic structure. So consider XH and XB with the horizontal and beta lift, vertical lift of the X, where beta running from 1 to n to n plus 1. So operating on this one, this vector in newly defined vector, sorry, tensor X beta, so P by 2 X beta, and this one we define, so we get this. Operating on X beta and X power H, we define here, then we get this value JHS X beta we define, and we get this one, number 18 and question number 20. Again, in the view of equation number 17, the tensor defined where so J we operate phi h x curl x, operate on equation number 17, we get this result. Equation number 21. And also we operate xi alpha and xi h, and this we have the result. After that, we calculate j square h and calculation after calculation p by 2 kx 2 sigma pq, we get the result pjx2. This shows that the newly defined tensor j is a metallic structure. So this metallic structure is j square equal pj plus q discard. So this shows that j is the metallic structure. First theorem is first. So next is the Riemannian manifold. Let M G be the Riemannian manifold, and we have the some rules. G. This is the diagonal lift G D of G. This is the diagonal lift of the metric G. So we have the rule, this one. The following rule we will use. This causal formula. And we have the following rules. We will use this. So let the frame bundle Fm of M admit a tensor J of type 1 from equation number 1 defined in equation number 17. Then GD is a metallic Riemannian metric. So G is the Riemannian metric. For now, we have to show that the diagonal of the metric G is a metallic Riemannian metric. So this is we have to prove this. So to prove the identity, this one, so enough to prove or enough to check the identity, x, we choose the 3 power, x power h, y power h. And we have to show that this one. This already easily we can prove that. So, and next one, x beta and mu, and alpha and beta. We take here and then we prove that this is in this form. This P, GD and QGD. This is the called metallic. If this satisfies, then it becomes metallic Riemannian manifold. And third case is, second case is here H, in the mu place H, beta H, and here also third place x by beta and mu. And second case is H here. See here, x beta j h, here H given. In case 2, sorry, or case 2, this case 2, beta and mu. Case 3, beta and H, then by mistake written mu, beta and H. So beta and H here written, so we get 0. So this satisfies. So we satisfy these 3 equations. If 0, no problem. Here 0, then we satisfy this equation. This 3 equation. GD equal PGD plus QGD. In this both 3 cases, 0 also satisfies this. So another formula for the 2 form. This, and consider 2 form F of the on the frame bundle. We also define the 2 form GD equal this. This is the 2 form on the frame bundle. F GD equal this. So we start here on the frame bundle. Fm of the manifold M admit the newly defined tensor J defined in 17, then 2 point here, 2 form F also we prove this one. Fxh and Fx 3 cases. These 3 cases I already proved here in the 2 form. In the case of 2 form, so 2 form of of any function f already defined in the on the frame bundle. Here this proof given, no need proof here. So another derivative of the two form. Derivative of let Fm be the frame bundle of M and the diagonal lift GD of metric G. Then derivative of two form also here defined. The case three cases X power H, H and H. Case number 1, we solve this one, this proof. Long calculation. Here this one 1 and 2 3 also given here up to 4. There are 4 properties given, so we prove this, use this formula, this 3df1 this one, and we get the formula, this 3 formula 1, this proof 2 3 and this 4 we already proved. Using similar device we can, so we find that derivative of two form also are established, these two. Also co-derivative of also defined here. Now some calculation, after that the some calculation for Nice-High tensor. This. Let x and y be the vector field on Fm and n be the Nice-High tensor of the vector tensor field J is given by this one. This is the Nice-High standard Nice-High tensor. So we have a theorem. Nice-High tensor of tensor J. We have still time, some time we have. Dr. Majid?
You have 5 to 7 minutes more.
Okay, no problem. Inshallah. See, so Nice-High tensor I also define here. Nice-High tensor. There are 3 cases. H, H, horizontal lift both. In both slot, horizontal lift, we satisfies here, this proof this. This is just proof. It's the theorem. This one, this long calculation actually. And here, alpha, beta, second. We have this proof. And third is H and beta. So horizontal lift and vertical lift. Here, in both slot, vertical lift. Here, both slot in horizontal lift. We prove the Nice-High tensor like this by of the newly defined tensor on the frame bundle. This 3. The proof is actually obtained by using this formula just written here. Now some application. In this section we study the diagonal lift GD of the metric G is the metallic Riemannian manifold with respect to JH, horizontal lift, and prove that this is locally metallic Riemannian manifold. So we consider here M be the differential manifold and Fm its frame bundle. So we define a GD, a tensor field, GD given like this. This is the local component of GD. And I will use this formula. Let J be the metallic structure and G be the metallic Riemannian manifold. Then GD is a metallic Riemannian manifold on the frame bundle. We saw that this. So this is the proof. And here one more theorem I here. We use first. We use 2 proposition for this one. Let F be the tensor field of type 1,1. Then horizontal lift is given by this, then del F equals 0, then horizontal lift also 0. And also this proposition, del H GD equals 0. This one. So it's become flat. So we have the theorem, let M be the locally metallic manifold and let JH be the, and GH is a horizontal and diagonal. This is D here by mistake. Diagonal lift of J with respect to them. Then Fm, JH and GD is also locally metallic manifold, Riemannian manifold. So also we have one corollary, and these are the references. This is my recently published paper on the frame bundle. This one, novel theorem for frame bundle. Actually, this talk on this paper. This and integrability of the frame bundle. Also, this is the metallic structure. Two paper published on many frame bundle, and other is now recently published this paper on tangent bundle. This 3 paper recently just, and other you can see other paper also. If you need, then you refer the many other tangent bundle paper, and we use this. And one more thing I want to tell, if beginning for tensor and their application you want to study, if anyone, then this book I have written in 2006, tensors and their applications, you can follow this. So any question? And thanks. Professor Abdul.
Hello. Hello.
Yes, sir.
Hello.
Nazrul.
Yes, sir.
First of all, thank you to Majid so that I can see the Nazrul after a long time.
Yes, sir. And if you open your video, then I can see you also.
I can open, but at present I am not. No.
Yes, sir. Yes, sir.
Yeah, I have much pain on me.
Don't worry, sir. We'll cure inshallah soon.
Yes, sir. Okay, I will join with my desktop.
Okay.
Hello.
Hello.
Viewers have some questions they can ask. I think we have 2 questions in chat box.
Okay.
From Pahir Ninju.
One minute, sir. What kind of the bundle? Actually, there's n+1, n+2 we not discuss here, and this depend on the dimension of the manifold. But what kind of the name? Actually, this frame bundle maybe of order n+1 you can say, but not now. Here this is depend on the dimension of n, dimension of the manifold M. Okay. So what type of the name is actually frame bundle and tangent bundle? There are 2 type of the bundle here. So n+1 and n+2 and so on. So maybe its name may be frame bundle of order n+1, but I don't know now what name is. Actually, this depend on the dimension of n, dimension of manifold. So n dimensions, so n frame bundle of dimension n. So maybe we can say that frame bundle of manifold M in the dimension of n+1. Maybe this kind. And the quadratic equation in slide 12, PQ are real number which are complex. Yes, if the real number, so only I take the real number with complex number, you can the quartile may be this. But here I consider as a real number and consider the P and Q, the positive integer in the case of metal. And maybe this complex, if you take complex, so this quaternion may be this one. Yes, possible this. I hope you got the answer.
Actually, I'm sorry, Professor
Yes, yes.
Professor Najum. May I answer this question on your behalf?
Yeah. Please.
Tahir, actually, up to now, nobody has studied the complexities of P and Q. Only reals are studied by Adara Blaga and Red Kanu. So complexities have not been studied up to now. Thank you.
Thank you, Majid.
Okay, thank you very much for such a nice and knowledgeable talk for research and academician who are working in the same domain. Thank you.
Okay, thank you. Thanks for kind words.
Now, Dr. Majid, our next speaker is Professor S.K. Srivastava, but we have left one Professor Beljilalji,
Sir,
so who will deliver
sir,
the lecture now.
No,
Can
Professor.
we consider once again Beldilali or Professor S.K. Srivastava?
Sir, Beldiji Ali will be delivering his lecture at 12. In place of Professor Najrul Islam, I have conveyed the message to him. Now the turn is of Professor S.K. Srivastava.
Okay, thank you.
Professor S.K. Srivastava is there, I think. He's ready.
Okay, thank you. Okay. So before starting lecture, I will say something about Professor S.K. Srivastava. Professor S.K. Srivastava is currently professor in the Department of Mathematics and Statistics in Deen Dayal Upadhyay, Gorakhpur University, India. Professor S.K. Srivastava working in differential geometry, green relativity, functional analysis, and Professor S.K. Srivastava has more than 20 years teaching experience in different universities. Professor S.K. Srivastava supervised 8 PhD and 5 students are working under him. Professor S.K. Srivastava completed 6 minor and major research projects. Professor S.K. Srivastava is a member of many professional bodies like Indian Science Congress Association, Bharat Ganita Parshad, and many more. Professor S.K. Srivastava has been published many research papers in national and international reputed journal. Professor S.K. Srivastava has been written 9 books, organized many seminars, workshops, and delivered more than 50 talks in different conferences and workshops. Now, I request Professor Srivastava that he delivered his talk. Professor S.K. Srivastava.
Thank you, Afroz. Can you hear me?
Yeah, your voice is a little coming.
Oh, okay. Thank you, Afroz. Actually, in my desktop, there is no camera. So, can I start?
Yes, sir. Start. Please start. You have to make, I think, is my slides are visible? Yes, slides are visible.
Okay. So I will talk about the gravitational collapse and space-time similarity. It's a simple. This lecture is not any research paper. It is just for the who be doing work at the beginning level. Conceptual lecture is there. You have taken actually. What I feel that the lecture is for PG students or those researchers who have started the work just now. So we will talk about the gravitational collapse and space-time similarity. Some basic concepts are there. In this one, we take origin of a universe, state, space-time fabric, creation of hydrogen and helium, formation of star, how the stars are formed, gravitation in classical physics, Newtonian physics, gravitation is not a force, whatever, and gravitational collapse, and most important, Schwarzschild's radius, black hole, and space-time singularity. So all of you know about the Big Bang theory. That Big Bang theory is the cosmological model of the observable universe from the earliest we know. This theory is proposed by Gamow and McKay, and according to this theory, it is believed that long ago, I think about 20 billion years ago, all the galaxies comprises the universe. At present, all the galaxies who comprises the universe were very close together and forming rather one concentrated mass and having temperature of order, I think 10 to the power 10 or something like that. And what happened that? At that time, one cosmic event takes place, and that is big explosion. And that explosion is known as Big Bang. And different concentrated matter were blown off from the galaxies, and since that the galaxies are going for the expansion of the universe. Then I use blackboard board also. So in Big Bang theory, what happened? The universe expanded from an initial state of high density and temperature. You know, in present when Einstein and de Sitter given his model, that is a static universe, what they feel that the universe is static. But after the Hubble, when Hubble gives his observations that galaxies are going far away from each other, then we have the concept of the expanding universe. Then after the initial expansion, an event that is by itself called the Big Bang, the universe cooled sufficiently to allow the formation of subatomic particles and their later atoms. Giant clouds of these primordial elements, mostly is hydrogen with some helium and lithium. After this Big Bang, we have actually what is important in that. It is important that the Hubble constant and that V is equal to HR, you know, one I use board. Nazrul sir, how can I use the board? Nazrul sir?
Hello.
Afroz, I want to actually I want to share the board so that I can write something.
There is a share screen green button below. If you click that, then it will show you option of sharing the whiteboard. There's in the Zoom window, there's a share greenish button on right below.
Just adjacent to chat box, share green screen button. When you press it, then we will see the whiteboard.
or on your slides where you are sharing your slides, there you can go into annotate and write there with a pen. If you can share your slides.
My slides are visible or not?
Yes, it's visible now. Your slides are visible.
But I could not share the board, unable to share it. Okay. So, what happened during the Big Bang for origin of universe? Actually, I want to clear about the Hubble relation. One Hubble relation is U is equal to HR, in which H value of H is 1.6 into 10 to the power 4. From that, we calculate the critical distance. That critical distance means since the light from galaxies at a distance equal to or greater than this critical distance can never reach us. So what is the boundary of observable universe? From that we calculate the boundary of the observable universe from where we can see the things, and that is distance is 2 into 10 to the power 6 light years. That is the observable universe, that is the critical distance from which we can see it. You can see this Big Bang event. Big Bang is an event which started with time. Before Big Bang, nothing can be measured that we feel, but according to Hawking and some other cosmologists, we can measure. Big Bang is what they conclude in their research, that this is Big Bang is the cycle. Big Bang cycle we have Big Bang and then Big Crunch and again Big Bang. So something is there before the Big Bang also, but we cannot measure it. Due to Big Bang, the continuation of time happened with further explain the existence of time. Now the space-time fabric. One more theory is there, steady state theory, which is given by Bondi and Gould. The Bondi and Gould, what they say, Bondi Gould say that the hypothesis is that the universe may not only be homogeneous, appearing the same from the all points at a given cosmic time, but may also be unchanging in time.
Hello, sorry to interrupt you. Sir, your slides are not moving. Your slide is stick only. First slide is seeing to viewers.
But in my, okay, but in my
I think
it's moving.
Yeah, it's visible.
But in my it is going on. So now what I am saying that the second theory, which is given by Bondi and Gould in 1948, they put forward the hypothesis that the universe may not be homogeneous, appearing the same from all points at a given cosmic time, but it may also be unchanging in time also, and that such universe would have no beginning or end and would continue forever in same steady state. That is the steady state theory. And when you see the steady state theory, the hypothesis given in it, that is similar to the Big Bang cycle. What is the Big Bang cycle? That after the Big Bang, we have a big crunch and then again Big Bang. And the same thing is given by the steady state theory, that it would be continuing forever in the same steady state. But in steady state theory, what they say, in this theory, the mass density rho is constant, and any co-moving observer at any point in space and time will observe the same Hubble recession. That Hubble recession is constant for every galaxy. That is the main drawback, you can say, of the steady state theory. Actually, what happened, these two requirements are of course not compatible with Einstein theory. That's why this theory is not so much, we can say, acceptable to everyone, because it is not compatible with the Einstein theory. Therefore, what the Bondi and Gold, they modify the Einstein theory to obtain the theory for which the divergence of energy momentum tensor is not necessarily zero. So that they have done in 1948. In physics, what happened? In physics, space-time is a mathematical model with 3 dimensions of space, x, y, z, t, and 1 dimension of time, fused together into a single 4-dimensional manifold. And space-time fabric is a combination of the 3 dimensions of space with 4 dimensions of time. In ordinary space, in terms of Cartesian coordinate system, the points are specified by x, y, and z, all of us know. Now in space, the position in the space-time is called an event. Now it becomes x, y, z, t. Thus, space-time is a 4-dimensional manifold. Now look at there. This is x, y, then x, y, z, and this is 4D. You see how the curvature of you can obtain in the space-time. Whenever you put any object on it, this flat spaces becomes curved. This is a 4-dimension space-time. Why are we taking time along with the space coordinates? Because simply the space is nothing without time, and time is nothing without space. So together, to balance the continuation of the universe after the Big Bang, it is mandatory in a way to take space and time together to make the space-time fabric. Now the curved space-time. You know that when this curve happens, when you put some mass on it, on flat space, when you put some mass on it, it becomes curved. So mass tells space-time how to curve, and space-time tells mass how to move. Right? When it is moving here and there, this curve is this space becomes curved here, and wherever this mass is moving. A massive body causes the space-time fabric to wrap, somewhat like the effect of a bowling ball placed on a rubber sheet. You can see. The creation of hydrogen and helium. Finally, the abundance of the light elements, hydrogen and helium found in the observable universe, are thought to support the Big Bang model of the origin. The Big Bang model of the origin of universe. 3 seconds after the Big Bang, we have so many conclusions the origin of universe from Big Bang theory. 10 to the power minus 14 second, what happened? 10 to the power minus 12 second, what happened? Because 3 seconds after the Big Bang, when the universe was billion of degrees in temperature, protons and neutrons combined to form what will become the nuclei of elements, mostly helium and hydrogen. That is the first element were formed as nucleus of hydrogen atom. Now the formation of a star. Star formation is a process by which dense regions within the nuclear clouds in interstellar space collapse and form stars. When one by one they cool down, and then we get the star. Molecular clouds, also called nebula, are the dense concentration of the interstellar gaseous atom and dust, helium atoms. One theory I forget to say, that is the first is Big Bang, then steady state, and one more theory is there, holy numerical theory, that is C field theory. C field means creation. Creation, what of creation? The creation of matter. In C field theory, we have the creation of matter, but that C field theory has some limitation. What type of limitation? We are not having the quantitative relation connecting to helium to the mean density of the universe. And you know about the Friedman-Walker metric and Friedman cosmology also. We do not have any physical theory for such an important phenomenon as a continuous creation of matter. That's why we does not study this as a long. And Bondi and Gold appreciated the fact that about this creation of matter. Then you have action principle and all that. So a few minutes after the Big Bang, the first nuclei were formed. That is, few minutes means 10 to the power minus 12 seconds are there. A few minutes after the Big Bang, the first nuclei were formed, after which the universe expanded and cooled to a point at which the high energy collisions were taking place, leaving the universe containing about 75% of hydrogen and 24% helium. Stars are giant nuclear reactors. The enormous luminous energy of the stars comes from nuclear fusion process in their center. In the center of a star, hydrogen atoms are taken apart by atomic collision and form heavier atoms elements that alters their atomic structure and release an enormous amount of energy. That helium, that this hydrogen atom combined together, that helium, and with this helium we have a large amount of energy. And then this hydrogen and helium gives the lithium and very hard, and helium, beryllium, and so on. Star fuse light elements to heavier ones. धीरे धीरे क्या हो रहा है कि combined होके heavier elements जो हैं, elements to heavier ones in their cores, giving off energy in the process known as stellar nuclear synthesis. Since the iron group is at the peak of the binding energy curve and heavier elements are created in the star by another class of nuclear reaction. This nuclear synthesis of elements heavier than the iron uses energy rather than supplies it. the enormous luminous heat and energy released during the nuclear fusion process make stars hot and bright. And due to this energy, the temperature is so high that they are not fit for our, you can say, for living and all that. What in classical physics, gravitation in classical physics. In elementary classes, we learned about the gravitation and the universal law of gravitation. You know, as G m1 m2 upon r square. The simple thing is that it is said that when Newton was sitting under a tree and apple fell on him, the fall of apple made Newton start thinking. He thought that if the earth can attract an apple, can it not attract the moon? Is the force the same in both cases? Then he gave the universal law of gravitation. In our solar system, all the planets go around the sun. We can say that there exists a force between the sun and the planet. From the above facts, Newton concluded that not only does the earth attract an apple and the moon, but all objects in the universe attract each other. And this force of attraction between objects is called the gravitational force. And he gives the formula that F is equal to G m1 m2 upon r square. After all the scientists were working, Newton conceived that there could be a single universal system of mechanics that could describe earthly and celestial motion at the same time. So he came up with the three laws of motion. You know all the three laws. An object remains at rest, law of inertia. An object velocity momentum changes with time in proportion to the force acting on it, F is equal to ma. For every action, there is an equal opposite reaction. Gravitation is not a force. Einstein said there is no such thing as gravitational force. Mass is not attracting mass over a distance. Instead, it's curving space-time. If there is no force, then how do you explain acceleration due to gravity? Objects should accelerate only when acted upon by a force. Otherwise, they should maintain a constant velocity. Curve of space-time is gravity, or gravitation is a bend in space. There is a contradiction between the Newtonian theory and Einstein theory, what they. Now the main thing, the gravitational collapse. Right? Before the gravitational collapse, we must know about the black holes also. Gravitational collapse is the attraction of an astronomical object due to the influence of its own gravity, which so many researchers are doing work on this gravitational collapse. You can see my papers also in International Journal of Geometric Modern Physics. There are so many, 5 or 6 papers are there on gravitational collapse of my. The gravitational collapse is the contraction of an astronomical object due to the influence of its own gravity, which tends to draw matter inward towards the center gravity. And gravitational collapse is a fundamental mechanism for structural formation of universe. जो हम बिग बैंग साइकिल की बात कर रहे हैं, उसमें क्या होगा, यही ग्रेविटेशनल कोलैप्स ही काम कर रहा है. कि सारे जो बड़े वाले स्टार्स हैं वो छोटे स्टार्स को अट्रैक्ट करेंगे, वो उनके उसमें आएंगे। आखिरी में क्या होगा कि एक कोई फिर हमें ब्लैक होल मिलेगा, सिंगल ब्लैक होल विच कंटेन्स ऑल द black holes inside it, and then we again have a big crunch. At the early stage of a star, with the hydrogen atom, burning nuclear fusion process occurred in core of star, and huge amount of heat and energy released. The released heat and energy produce outward thermal pressure, which balance the inward compression caused by the gravitational field of massive star. The star then exists in a state of dynamic equilibrium with balancing with inward and outward pressure. कोलैप्स कैसे होगा देख लीजिए, जब ये अंदर वाली चीज इसको ऊपर वाली चीज जो है अंदर बैलेंस करने के लिए पूरा नहीं कर पाएगा तो क्या होगा, इट विल कोलैप्स इन द कोर ऑफ द स्टार. In the nuclear fusion process, when all the hydrogen atom has burned and formed heavier atoms like helium and lithium, in the next stage, the nuclear fusion with these heavier elements produces fewer amount of heat and energy. धीरे धीरे वो कम होती जाएगी, स्टेडी स्टेट में वो आता जाएगा. Once all its energy sources are exhausted, when only heavier elements like iron, Au exist in the core of a star, nuclear burning of heavier elements produces very few amount of heat and energy. A star will again collapse until it reaches a new state. The Schwarzschild radius, 2gm upon c square, where g is the gravitational constant, m object mass, and c the speed of light. It is a physical parameter that shows up in the Schwarzschild solution to Einstein's equation corresponding to the radius, defining the event horizon of a Schwarzschild black hole. Just a minute. Yes. हाँ बताइए. हाँ सब. हाँ ठीक ठीक ठीक, अभी हम बात कर रहे हैं, अभी बात कर रहे हैं. Sorry. So this Schwarzschild radius defining the event horizon of a Schwarzschild black hole. The boundary of the region from which no escape is possible is called the event horizon. We have particular origin and event horizon. What is the event horizon? The boundary, and this boundary is defined by this Schwarzschild radius. Now, what is the black hole? You know the black hole, what the black hole does. The black hole partitions the three-dimensional space into two regions. One region is this external and this is internal. An inner region bounded by the smooth two-dimensional surface called horizon. The region outside the horizon which is asymptotically flat. And the essential characteristic of the black hole is that the inner region cannot communicate with the outer region. Even the light cannot escape from it. And it can be said that at the origin, the gravitational field is so strong that even light cannot escape. This is the let us take an object with radius r. So if we compress this object, its volume will remain same. So now when r is equal to rs, this Schwarzschild radius. escape velocity is equal to speed of light when Rs is greater than R. And escape velocity greater than speed of light, then this is the condition where black hole is formed. How they form, right? You know, if sun is black hole, when the sun becomes a black hole, an object with the mass of the sun, means mass of the sun have radius 2.5 kilometer. You know the radius of sun. And similarly, in case of Earth also, the radius of our Earth is supposed to be 6,400 kilometers. When it becomes the object of 2 centimeter radius, or you know that so much energy is condensed, then it becomes the black hole. For making the Earth black hole, it becomes the object of 2 centimeter radius. So you can just imagine how much energy is inside it. Even the due to that energy, even the light cannot escape from it. A black hole is a region of space-time where gravity is so strong that nothing, neither massive particle nor massless particle such as light photons, can escape from it. Black hole is a region of strong gravitational field. Now the space-time singularity. The space-time singularity. My voice is coming, Afroz sir?
Yes, sir.
Afroz,
Voice
sir?
is coming. Yes, sir. Voice is coming. But you have 5 more minutes to complete your talk.
Actually, Majid, I have so much pain on my neck and this, right? The 5 minutes, okay. Yeah, I will take.
Okay, sir. So, sir,
actually,
please
I could not go through the board. That is the main thing, is that space-time singularity. A space-time singularity is a condition in which gravity is so intense that space-time itself breaks down. This one. So space-time singularity is a condition in which gravity is so intense that space-time itself breaks down. As such, a singularity is no longer a part of regular space-time. Right? We can also say that the space-time singularity is a point in space-time where laws of physics break down. That is, T is equal to 0 when we start. Okay. So for black hole, we have small size exterior solution, and then we calculate some RS and all that. Spherical and non-spherical gravitational collapse are there. And one important thing is the Price theorem and Kerr metric of the rotating black holes. And non-spherical gravitational collapse is also very important. So condition for the black hole, you know that R is equal to Rs, and the present a time and energy barrier to any outward signal from the collapsing object. When this stage reaches, the object is said to have become the black hole. So in practice, we would like to know how a collapsing body of irregular shape and angular momentum would behave. Means collapsing stars may rotating and hence be non-spherical in shape. So non-spherical for non-spherical gravitational collapse, we have a good one Kerr metric and Price theorem. Price theorem, they consider the case of collapse with the small non-spherical black holes. Okay, Majid, we conclude. But after a long time, I am using this, so I could not manage the black my whiteboard from here. But in that, we have to give some conclusions. Okay. Uh, and thank you for inviting me, Afroz sir and dear Mazid, to
Okay, thank you very
give the
much for
lecture
your
in this.
nice and knowledgeable talk for researcher and academician who are working in your domain. Thank you very much, sir. Now, if viewers have some questions, they can ask.
If you have question, then I can.
I have a question. May I ask?
Yes, sir.
Yes,
Yes,
sir,
please, sir.
yes.
Uh, what's the order of magnitude of stars? What is the mass of the star for it to fuse
In a black hole.
to iron in the center and become a black hole?
Become,
What should be the
sir,
order of masses?
become a black hole.
Yeah, what should be the mass of star which could finally end up as a black hole?
That I have given,
Theoretically.
that I have given the example of sun and earth also.
No. But the sun will never collapse to become a black hole. Yeah, it will just fuse up to helium and stop there. It will become a helium dwarf star.
Yes,
But
yes.
theoretically, what are the masses required for it to become a black hole?
Sir, mass is required for a black hole. That I have told, the whatever the mass of the sun is there, and when it becomes the mass of the sun, when whole mass of the sun has a radius in radius 2.5 kilometers is condensed,
Yeah,
then
that's
it will
right.
be the.
That I agree, I accept. I'm saying what kind of stars, what should be the initial mass of stars be so that it can finally end up as a black hole? What mass should it start off with? Our sun will not become a black hole. Our sun will just fuse hydrogen to helium and stop there. It will not go into the other stages. So what should be the masses for it to
It would be a black
fuse
hole.
then carbon, magnesium, all the way up to iron? So what should be the, theoretically, I'm asking mathematically, what are the estimates
Order of the
you
mass,
have?
sir, order of a mass of any star to become a black hole. That you are asking, I think.
Yes, what should be the initial mass of a star which could end up as a black hole?
So that is not determined, or you can say that is not fixed. For different type of different black holes, whether it is Cygnus X1, that is the, or you can say Cygnus X1 or Scorpio, they all have the different all have the different masses. So but I think that this mass is not actually defined the order of the mass to become the black hole. In case of sun, I say it would be a black hole. When whole mass of the sun has reduced 2.45 kilometers, it would be a black hole. But the order of mass to become a star as a black hole is yet not defined.
Okay.
Okay, Afroz sir.
Okay, thank you very much, sir. I really appreciate the golden words you have explained in such a nice way and shared valuable insight with us. I am thankful to you for prudent opinion. Thank you very much for such a nice and knowledgeable talk for the researchers and academicians who are working in the same domain.
It is
Thank you
actually
very much.
a very basic lecture for the student just starting the research, so that they know about these things, simple things. It is not a very high level research paper, because what I think that the audience are the PG student or research student. That's why I give this type of talk.
Okay, thank you. Thank you.
Okay, next one is.
Thank you, sir. Thank you, Afroz Saab, for chairing the session. It was wonderful session, and eminent speakers like P.K. Sahu, Professor Srivastav, Professor Najrul Islam Saab delivered a wonderful talk. Thank you all. And now Professor S.K. Srivastav will chair the session. So, and speaker of the session is Professor Belji Ali. Are you there, sir? Thank you, sir. Thank you, Afroz sir, for chairing the session. It was a wonderful session, and speakers like P.K. Sahu, Professor Srivastav, Professor Najrul Islam sir delivered a wonderful talk. Thank you all. And now Professor S.K. Srivastav will chair the session. So, Professor Belji Ali, are you there? Professor.
Yes, sir. Professor Beljile is there. So we can start, I think.
Yes.
Can you hear me?
Sudhir sir, over to you, sir. Sudhir sir,
okay,
over to you.
Oh, thank you. So we have in this session Professor Belji Ali. He is Associate Professor in the Department of Mathematics, University of Mascara, Algeria. And he's doing the wonderful work. His research interest is in differential geometry, Riemannian geometry, structure on manifolds, symmetric properties. He published so many papers in the international and national journals, and doing the very good application work on the differential geometry, which is the need of the present time, right? And I request him to start his lecture, Professor Belji Ali.
Yes.
Sir, please, you can start.
Okay. Assalamu alaikum.
Wa alaikum assalam.
Firstly, I would like to thank all the organizers of this symposium. Secondly, I apologize for my poor English. So, and for my bad connection, the weather is not good here. Okay, my presentation is titled Bridge between elementary three-dimensional almost contact metric structures. This presentation, we present the elementary three-dimensional almost contact metric structures, and we introduce a class which generalize them. Then we give some techniques to construct any structures from another on the same manifolds. The first section is some definition on the almost contact metric structure. Always M denote a three-dimensional Riemannian manifold. The data var phi, xi, eta is an almost contact structures if the two condition is fulfilled. Eta is one form, xi is a global vector field, and var phi is a one tensor field. The condition of compatibility, number two, the data var phi, xi, eta, g is called an almost contact metric structure. For any structure, almost contact metric structures, we can define a fundamental two form phi by this formula. And for the normality, the tensor n1 equal n phi plus 2 eta xi. If n1 equals 0, we say that the structure is normal, where n phi defined by this formula. And if the tensor n var phi equal 0, we say that the structure is integrable. So if n1 equals 0, the structure is normal. If n1 different 0 and n phi equals 0, we say that the structure is integrable. Okay. For the second section, we introduce a generalized Transazakian manifolds. In Gonzalez and Chinia-Gonzalez classification of almost contact metric structures, there are 12 classes. But in dimension 3, there are only 5 classes. Classes of cosymplectic and class of beta Kenmutsu and class C6 of alpha Sasaki. These 3 classes are normal. It means that n1 equal 0. And the 4th classes is C9. This class is just properly almost cosymplectic, because in this class is not normal and not integrable. And the 5th class is C12. We call it corner manifolds. This class are integrable but not normal. So the 3 first classes, cosymplectic, beta Kenmutsu, alpha Sasaki, Ubina generalized these 3 classes by this class, Trans-Sasaki, C5 plus C6. And this class is characterized by this formula, nabla x xi, nabla is the Levi-Civita connection, equal minus alpha var phi x minus beta var phi square x, where alpha and beta is 2 function on M defined by these 2 formula. For the C9 is not an important manifold classes, because it's just an almost cosymplectic. For the corner manifolds, C12 is characterized by this condition, nabla x xi equal minus eta x psi, where psi is a global vector field equal minus nabla xi. Remark here, if the structure is normal, automatically nabla xi equals 0. And there is no psi, then the class never be C12. Okay, the goal for our generalization is to study the class C5 plus C6 plus C12 together, and we construct bridge between the elements of this class. We have this remark. Trans-Sazakian class is characterized by this formula, and corner structure C12 is characterized by this formula, always with psi equal minus nabla she. We give a definition. Hello, you hear me?
Yes, you are audible. Use.
Okay. The first definition: any structures from or element from the class C5 plus C6 plus C12 is said to be a generalized Transazakian structure, and it's characterized by the formula 7, where alpha and beta and gamma is 3 function. Gamma is the length of psi. So we called this class generalized Transazaki of type alpha, beta, gamma. For the existence of this class, to prove this the existence, we give a class of examples. In the Euclidean space, we give a Riemannian metric with 2 parameters, rho and tau, 2 functions on R3. And we define the structures var phi like this, and she and eta. One can check that the data phi, she, eta, and g is almost contact metric manifolds. We give a frame E1, E2, E3, and the necessary components of the Lefis beta corresponding to G are given by, we want nabla X, she. It's mean nabla E1, she, nabla E2, she, and nabla she. Where rho E, it's mean the partial rho respect to X, E. Okay. On the other hand, we have the right term minus alpha var phi E1 minus beta var phi E1 minus eta E1 C equal this expression, and for the E2 and for she. We compare with comparison between 11 and 12, we can see that our formula, our condition for generalized Transazaki. So we say that our structure is generalized Transazaki manifolds if and only if alpha equal rho 1 minus 2 derivative over 2 tau rho, and beta equal rho 3 rho, and gamma equal this expression, if and only if this condition is fulfilled. So this class of examples prove the existence of such class of almost contact metric. We give here an interpretation for this generalization. For an almost contact metric structure var phi she eta g and a smooth function sigma on M, we have this transformation. The conformal transformation is well now. So the new structure var phi tilde and she tilde and eta tilde and G tilde is also again an almost contact metric structure. But this idea does not work well for the Trans-Sazakian structure. It means that if the initial structure is Trans-Sazakian, the deformed structure is not necessarily Trans-Sazakian. Okay. Look at this definition. The manifolds M var fichier eta is said to be locally conformal Trans-Sazakian, briefly generalized Trans-Sazakian of type alpha beta if the resulting almost contact metric manifolds by conformal transformation is Trans-Sazakian of type alpha tilde beta. Okay. On the other hand, we know that the connection of Levi beta for the metric G and G tilde is related by this formula 16. If we put D sigma equal omega one form, is the exact one form, we get this formula 7 from 16, where psi is a vector field defined by this formula. So if the deformed structures var phi tilde, she tilde, eta tilde, G tilde is a Trans-Sazakian, then we replace nabla tilde x she tilde here, and we extract nabla x she, we get this formula, our formula. Okay, we have then an interpretation for our generalization. We give here a theorem for to characterize this generalization. For any three-dimensional generalized Trans-Sazakian manifolds of type alpha, beta, gamma, we have d phi fundamental two form equal to beta, eta, wedge, phi, and the eta equal omega wedge eta plus alpha phi, and n1 equal to omega wedge eta tonsorial she. Then we pass to section 2 to give some transformation of generalized Trans-Sazakian manifolds and some techniques to construct bridge between the element of this class. The beginning is with this deformation. We call it deomotitic transformation, generalized deomotitic transformation. Let var phi she eta G be an almost contact metric structure on M3 for any two function, smooth function, positive F and H on M. We put var phi tilde equal var phi and eta tilde equal H eta, she tilde equal 1 over H she, and G tilde equal F square G plus H square minus F square eta tonsorial eta. Remark, var phi is not deformed, just var phi is not deformed here. Var phi tilde equal var phi. So the structures Varphy tilde, she tilde, eta tilde, g tilde is again an almost contract metric structure. Is well known dissociates. Okay. But this transformation generalizes all the special cases that have been studied so far. For example, for h square equal f square, we get the conformal case. And for s square equal f square equal f square, no, equal f 4 here 4, h square equal f4, and f square equal a is constant. We get the case of tunnel. And for h square equal 1, we get the case of Marrero. For h square equal f square, we get the case of Blair. So, using the Cotzil's formula on this deformation to get the connection nabla tilde, we get this formula. Suppose that the initial structure is generalized Transazakian structures of type alpha, beta, gamma. The initial structures is generalized Transazakian. This formula becomes like this, 21. We can extract nabla tilde x she tilde from this formula using the condition of generalized Transazakian structures. Look at this formula. We can say that this is alpha tilde and this is beta tilde and this is C tilde, but it must, this term must be 0. For that, we have two possibilities. If h square equal f square, then this term equals 0, and we get just the conformal transformation. And the rest is a generalized Transazakian. And the second possibility is omega equals 0. It means that the initial structures is not gamma equals 0. Gamma equals 0. It's the generalized Transazakian of type alpha beta 0 if omega equals 0. So we give this theorem. If Varphy she eta G be a generalized Transazakian structure of type alpha, beta, gamma, then for h square equal f square, the deformed structures is the generalized Transazakian manifolds where alpha tilde equal alpha over f and beta tilde equal 1 over f beta plus she ln f and gamma tilde equal this expression. The second case, if f square different from h square and omega equal 0, then the deformed structures is a generalized Sazakian of type alpha tilde and beta tilde and gamma tilde. We can give a diagram to explain this position. Okay. Look at this diagram. This case is for H square equal F square. The cosymplectic we can get from the cosymplectic, another cosymplectic, or a Kenmutsu or a corner, but we can't get a Sasaki. From the Kenmutsu, we can get the cosymplectic with this condition and another Kenmutsu and a corner, but we can get Sasaki. If the initial structure is Sasaki, we can get another Sasaki, just another Sasaki. And if the initial structure is corner, we can get cosymplectic, Kenmutsu, corner, but we can't get a Sasaki. Here, we say that the corner is an integrable and the Kenmutsu and cosymplectic is normal. It means that we can get a structure, a normal structure from an integrable one. Look at this diagram. There are no bridge between Sasaki and other structures. For the second case, H different from F and gamma equal 0, omega equal 0, that the initial structures never be corner. So we get this diagram. We can construct cosymplectic Kenmutsu or corner from cosymplectic. We can get cosymplectic Kenmutsu and corner from Kenmutsu. And for the Sasaki, we can't get cosymplectic Kenmutsu corner. We can get just Sasaki for this condition. So always there are no bridge between Sasaki and others. For that, we give another technique to construct bridge between Sasaki and the other structures. So we give another transformation. We call it Varphy conformal transformation. For any almost contact metric manifolds, Varphy Xi eta G, and a one form theta orthogonal to eta, theta is orthogonal to eta. We give this deformation and remark that Varphy here is deformed. This deformation, in this transformation, we deformed the metric and the structural tensor Varphy together with using one form orthogonal to eta. We can prove that Varphy tilde, Xi tilde, eta tilde, G tilde is an almost contact metric manifold. The first remark, the metric can rewrite like this. This metric, we can, these two terms is just F, G, Varphy X, Varphy Y. And this, we transform this term in the left, we get G tilde, Varphy tilde X, Varphy tilde Y. And that is why this transformation is called Varphy conformal transformation. It's conformal because there is a function here, f, and with the Varphy here and here. Okay. For a second remark, if theta equals 0, we get the Mariro transformation. For this transformation, we study the normality, or we search for the relation between N1 tilde and N1. By a long but simple calculation, we can get this equation, number 23, where N3 here equal this expression. Okay. We have this proposition.
Professor, I'm sorry, but you are running out of time. Please wind up.
Yes, I don't understand.
Please hurry up, sir. You are running out of time, sir.
I don't understand.
Please complete, sir. Please complete.
I continue.
Please complete quickly, sir.
So, okay, proposition. Let N1 equal to omega when which eta tensorial she. It means that the initial structure is generalized Transazakian. Then the N tilde equal to omega eta tilde she tilde here, she tilde, if and only if d theta equal omega wedge theta plus lambda phi, where lambda is a smooth function. With this condition, we can get the nabla tilde x she. So using Cauchy formula, we get 24. We get this formula. And suppose that the initial structures is a generalized Transazakian, using the property of these structures, the eta here and nabla, and the eta tilde is just the eta minus the theta, because eta tilde equal eta minus theta. So we get this formula, 25. And we can see this is alpha tilde and this is beta tilde, and we can get here psi tilde equal Varphy tilde square psi with minus here. So we give this theorem. If the initial structure is generalized Transazakian structure of type alpha, beta, gamma, then the deformed structures is also generalized Transazakian structure if with alpha tilde, beta tilde, and this gamma tilde. We give this diagram for our four elementary three-dimensional almost contact metric manifolds. It means with Sasaki, Kenmutsu, corner, and cosymplectic. The green bridge is the bridge between Sasaki and Kenmutsu, Sasaki and cosymplectic. It means that this transformation resolves the problem, the above problem. Look at this diagram, Sasaki, with this condition, we get a cosymplectic. And Sasaki with this condition, we get Kenmutsu. And with this condition, we get another Sasaki. But the problem we can't get a corner. So there is no bridge between Sasaki and corner structures now. So it's an open question. Bridge between can one construct a bridge between Sasakian and corner structures? So this is our main references. This reference is about C12 corner manifolds. Here is a recent paper, and an important paper about normal almost contact metric manifolds, paper of Olshak. Thank you for your listening to me. Thank you very much.
Thank you, Professor Balziali, for the nice lecture. Because the generalized, actually, I am interested in generalized d-homothetic transformation. That is very important. Important, it is very good for the researchers, new researchers. They can go through it, and also that generalized transformation of trans-Sasakian manifold. Sir, thank you for the very nice and info lecture, and you have such a good results. And thanks a lot, and congratulations to you for this type of research. Thank you, Professor.
You're welcome. Thanks. Thank you, Professor.
Okay, Majid, it's over to you.
Thank you, sir. Is there any question or comment?
Professor Greece, can you hear my voice?
Yeah, you are audible.
Hello, dear my friend Chris. Thank you very much for your nice presentation. I have a question.
Hello, my friend. I'm my brother.
Hello. I have a question. You shared some diagrams and very good information content. My question is that we know that a Kenmatsu manifold is not Sasakian. It's because it's not normal. How can we construct a bridge between these two structures? Because Kenmatsu is a different class of contact manifolds, and its importance also comes from it is not Sasakian. You construct a bridge between these two structures under conformal, Barfield conformal transformation. Is it possible? How is it possible? I asked this question.
There is problem audio. I can't listen to your question. You can repeat, please.
Okay. How is now my voice? Could you hear?
Hello.
Could you hear me?
Please write your question.
Okay.
Write it.
Okay.
Just maybe I speak just to translate for Grisi. Grisi, donc ce qu'il veut dire, pardon me, I am speaking English, French, or in Arabic maybe. Ce qu'il a dit que la structure de Kenmatsu, normalement, c'est totalement différent par rapport à Sasaki. Comment vous arrivez à passer de Sasaki à Kenmatsu? C'était ça sa question. تفضل.
شكرا استاذ محمد. شكرا استاذ محمد.
تحيه خاصه. نعم.
الو Inan?
Yes, I can hear you.
Return to our diagram here.
Yeah.
From Sasaki, we can get the Kenmutsu. It's your question?
Yes.
I use this new transformation. This one is is published in a recent paper. You can you can download it. And in this paper there is concurrent examples to get Kenmutsu from corner and Sasaki, co-simplicity Sasaki. You can, okay?
Just remark very simple, quickly. Thanks, Conal, for the question. لحظة. There is a question is because Kenmetsu locally is a warfare product. For example, another question, another way, that how you can destroy this the warfare. This is well known that if you have one dimension with 2 dimensions, so we can get them in Sasaki quickly. But for him, we can say locally is a warfare product, the Kenmetsu. So not enough is not enough, for example, to make computations and after that to give examples, because to try, for example, from another way to be sure that is, for example, one question is for corner, Xi, is it killing vector field for corner, for example?
For
corner, yeah. For example, for corner, we said there is no normality, no integrability. Yeah, but you can in Sasakian is very famous. Red vector field is killing. This is another way. Maybe you can, for example, with your computations, maybe you make a contradiction. It's impossible, which means you continue your computations to maybe the question to answer exactly for the answer to Unal. Very happy. I'm very happy that Chris is working hardly these years. So thank you very much. And maybe I will leave because I have some. Thanks a lot. تحية خاصة Chris.
شكرا.
Thank you.
Okay. Thank you very much, each and everyone who contributed in this session. I'm thankful to Professor S.K. Srivastava for chairing the session and Professor Belji. Really, it was a very wonderful lecture, and you provided us a tool to how bridge can be made between Sasakian and the Kenmetsu manifolds. Really, it was wonderful lecture. So, on behalf of organizing committee, I'm very much thankful for delivering such type of wonderful lecture. Thank you very much, sir.
Thank you.
Okay, and the next session will be chaired by Professor P.K. Sahu, and he is already there, I think. And our next speaker is Professor Vishnu Narayan Mishra. He is also there. Actually, this lecture is one special lecture in the sense that because when we talk about approximation of higher order polynomial curves, and as all of you know that curves are one-dimensional manifold and curved surfaces with a low order one, so this plays an important role in data comparison and data transmission and data exchange. Basically, these all tools have very much applications in computer-aided design and computer-aided geometric designs. These 2 tools are being used in automobile industry and robotics. So this thing has become very popular nowadays, and that's why we have one special lecture for this to be delivered by Professor Vishnu Narayan Mishra. So, Professor Sahu, hello, Professor Sahu.
Yeah. So, good afternoon, all.
Yeah, Professor Sahu, over to you, sir.
Yeah.
Over to you.
Yeah. So, thanks, Dr. Majid. So, the next speaker is Dr. Vishnu Narayan Mishra. So, let me welcome Dr. Vishnu Narayan Mishra. So, Dr. Vishnu Narayan Mishra is working as professor and head Department of Mathematics at Indira Gandhi National Tribal University, Lalpur at Madhya Pradesh. So he received the PhD degree in mathematics from IIT Roorkee in 2007, and his research interests are in the areas of pure and applied mathematics, including approximation theory, variational inequality, fixed point theory, operator theory, Fourier approximation, nonlinear analysis, special functions, Q series, and so on. And he is referee and editor of several international journals in pure and applied mathematics. And also, it is noted he is editor and reviewer for applied economics journals also. So he has authored more than 400 research papers to his credits, published in various journals and proceedings. He has guided many postgraduate and 9 PhD students. He has delivered talks in various international, national conferences, workshops, refresher programs as a resource person. He is actively involved in teaching undergraduate and postgraduate students as well as the PhD student. He is a member of many professional societies, to name a few: Indian Mathematical Society, International Academy of Physical Sciences, Gujarat Mathematical Society, and so on. So Dr. Mishra received gold medal in BSc, double gold medal in MSc. Then he got VM Saha Prize in Indian Mathematical Society at BHU and Young Scientist Award in Punjab's Allahabad University, Prayagraj, and also Best Paper Presentation Award at Ghaziabad. So he is very well known and reputed in the areas. So let me welcome Dr. Vishnu Narayan Mishra. Dr. Mishra, this floor is yours now. Please carry on.
Thank you, Professor Sahu, for introduction about me. And I am very much thankful to the organizers of this prestigious symposium that is held at Department of Mathematics, School of Sciences, Maulana Azad National Urdu University. And it is Central University at Hyderabad. Especially thankful to, this is ISDGA-2022. And special thanks to Dr. Subhash and Dr. Majid Ali Chaudhary, Department of Mathematics, School of Sciences, Maulana Azad National Urdu University, Hyderabad, who gave me the chance interact with you all. And here we start some basic concepts of mathematical analysis, which is very useful in every branch of mathematics, like as either you do in differential geometry or fixed point theory. My voice is audible to everyone?
Yes, sir.
Okay. And this is my camera is.
Yeah, your camera is visible.
No. I have joined from 2 systems. That is, one is desktop and the other is mobile. But in my mobile device, the camera is not in front of me. It is back side. So I think that, yes. Perhaps now it will come.
Yeah.
It is. Yes, now it is working.
Yes, sir.
Okay. Yes. I clicked camera, that is it goes to other side. So here we start some basic concepts of mathematical analysis, that is mathematical tools, which is very useful in all branch of mathematics, like differential geometry, special functions, approximation by positive linear operators, nonlinear analysis with their applications, fixed point theory with their applications in dynamic programming, etc. Application of fixed point theory also. Approximation by summation integral type of operators also. Summability theory. So I am sharing my screen here. Here, I am working here as professor and head. Before professor and head, I served as associate professor in this department of mathematics, Indira Gandhi National Tribal University, Amarkantak, approximately 3 years. And before here, IGNT Amarkantak, I served as assistant professor of mathematics in Sardar Vallabhbhai National Institute of Technology, Surat, Gujarat. I served as assistant professor of mathematics for 3 years, 3 months. So, very much thankful to session chair, Professor P.K. Sahu, also. So, can I start my talk here?
Yes, sir.
Okay, thank you. Here we discuss that is degree of approximations mean error in approximation of signals functions using various types of summability transform methods in different spaces, and approximation of function by positive linear operators using quantum calculus will also be highlighted if time allowed. And during this talk, few applications of approximation of functions will also be highlighted. We are very much known what are the sequences and the subsequences. Let us recall this topic. Suppose S and T are two sequences in a set capital X. Then T is said to be subsequence of S if there exists a map phi from to n such that T is equal to S composition phi. And for each n element of capital N, there exists M belongs to capital N so that phi I greater or equal to n for every I greater or equal to m in n. Okay. For each n belongs to capital N, there exists a natural number in n such that phi I greater or equal to n for every I greater or equal to m in n. This is the subsequence. In other words, if we say that if Sn is a sequence in X and In is a sequence in n such that I1 less than I2 less than I3 less than and so on so forth less than In and less than, then Sin is called subsequence of Sn. Then Sin is called subsequence of Sn. For example, if we take Sn is equal to 1 upon n is a sequence in R, then what will be the subsequence of it? That is 1 upon 2n minus 1 will be subsequence, because if we define phi from n to n such that phi n is equal to 2n minus 1, then subsequence T is equal to S composition phi of n is equal to S of phi at n, that is S of 2n minus 1. And we have already taken that is Sn is equal to 1 upon n. So S2n minus 1 is equal to 1 upon 2n minus 1. That is 1, 1 upon 3, 1 upon 5, etc. are the subsequence of the sequence. 1, 1 upon 3, 1 upon 2, 1 upon 3, 1 upon 4, etc. These are the concept of subsequences. Approximation, especially Fourier approximation and wavelet approximation, have received great importance during the last few decades because of their use in modern technology with signal theory and data compressions in particular. Fourier approximation was originally evolved from the problem of divergence of Fourier series. Kolmogorov in 1926 has proved that Fourier series of a continuous function of period 2 pi can diverge almost everywhere, and thus summability theory came into its appearance. In summability theory, we attempt to assign a value, suppose small s, to an infinite series. That is, we try to generalize the concept of sum of any non-convergent series. We try to generalize the concept of sum of non-convergent series. And in summability theory, one attempts to assign a value, suppose s, to a given series that may not be convergent. That is, one tries to generalize the concept of sum of any non-convergent series. And in summability theory, it is a theory of assignment of limits, which is fundamental in analysis, function theory, topology, and functional analysis. In mathematical analysis, a summability method is an alternative formulation of convergence of a series which is divergent in the conventional sense. And summability is a field in which we study the sum of that is the non-convergent series or non-convergent integrals and assigns a value, a number, suppose small s to it. For instance, following are some interesting cases for which the assignment of limits can be done. Real or complex sequences for the limit process as n tending to infinity. Series, convergence of series, divergence of series, etc. So series, sequence and series of functions like power series, Fourier series, etc. In mathematical analysis, power series, Fourier series, etc. So limit of a function at a point, that is continuity, continuous extension, differentiation of functions, integration of functions. In 1890, Cesaro was one of the mathematicians who deal with the sum of some non-divergent series and defined Cesaro summation. In a specialized mathematical context, values can be objectively assigned to certain series whose sequences of partial sums diverges. This is to make the meaning of the divergence of the series. For example, this is the Grandi series, 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. And the Cesaro summation assigns Grandi series, that is the value 1 upon 2. And there exist three types of summability process, that is, one is ordinary, second is absolute, and the third is strong. Ordinary, absolute, and strong. How do we study this branch of mathematics? Because if your solution is just unstable, that is not stable, and your problem is neither convergent nor divergent, then such type of operator plays an important role to make the solution as stable as well as the problem that is there. Their summation can be found. It is summable. If your infinite series is neither convergent nor divergent, oscillate finitely, oscillate infinitely, then approximation of functions using summation or summation integral type of operators make the solution stable as well as summable. That is, your problem will be stable and convergence. It is summable. It is finite. Summation is finite by Cesaro operator, Nalund operator, etc. There are various type of operators. Approximation using summation type of operators are very much applicable as a tool for filter the signals in the form of series, infinite series, Fourier series, wavelets, etc. Using the various summability methods. Using the various summability methods such as matrix summability, Cesaro and generalized Cesaro, Holder, harmonic, Risch and Risch typical means Nalund, generalized Nalund, indexed, Abel, Euler, Borel, Hausdorff, Banach, etc. The aim of this study is to discuss the stability of the system using the summability and absolute summability methods. By using the advanced summability method, we can improve the quality of digital filters with finite impulse response in particular. Advanced, that is, we use the approximation by summation integral type of operators, then we can improve the quality of digital filters. In engineering sense, we say that the approximation of the signals with the help of summation methods is widely used in the digital filter, such as finite impulse response filters, FIR filters, and infinite impulse response filters, IIR filters. And these filters have numerous variety of applications, like in speech and image processing, communications, radar, sonar, and medical signal processing, etc. For an engineering problem is finitely differentiable data with jump discontinuities, there are more sophisticated ways to use the sampled data to obtain a more accurate solution using the approximation of the Fourier coefficients by summability techniques. Because there appear gives a phenomena in Fourier approximation, gives a phenomena that is the convergence of Fourier series is very slow near the point of discontinuity. At the jump point, it is very slow. Guess phenomena is an overshoot, a peculiarity of the Fourier series and other eigenfunctions at a simple discontinuity. So there are more sophisticated ways to use the sample data to obtain a more accurate solution using this type of operator. And with the help of minimal set of sufficient conditions for a soft computing model, the error can be minimized by using summability methods so that the output data is filtered and according to our interests for observing the behavior and the requirements of the modeled problem. There are various types of summability methods. Raplid was the first to put such methods systematically, and thus after his name they are called as T methods. And the T methods are based on the formation of an auxiliary sequence Tn defined by sequence to sequence transformation. Tn is equal to sigma k is equal to 0 to n a n k sk, n is equal to 0, 1, 2, 3, etc., where Sn is the n plus 1 partial sum of infinite series sigma un. Let us see transformation 1. If Sn is the input sequence of information and Tn is the output sequence of information, then T is equal to ank like behaves as a digital filter. T is equal to nk is a lower triangular matrix with real or complex numbers. And one thing more, that is this Sn is the input signal sequence and Tn is desired output signal sequence. Then T is equal to nk behaves alike as a digital filter. Trigonometric Fourier approximation and evaluate approximation have played great importance in stochastic engineering problems also. T is equal to nk being this lower triangular matrix. Tn is called a linear mean or matrix mean, that is output sequence of informations, and it is linear mean or matrix mean. Linear property we know very well. An infinite matrix, an infinite series sigma un is said to be summable to a finite number of methods if Tn converges to S agent tending to infinity, where S is a finite number, and the matrix T is said to be regular if Sn converges to S implies Tn also converges to S agent tending to infinity. Okay, and the necessary and sufficient conditions for the regularity of the Laplace matrix T is equal to nk are given by first condition, uniformly bounded summable rows. Sigma k is equal to 0 to infinity mod nk is less than m, where m is independent of n for every n. Where m is independent of n for every n. And limit n tending to infinity nk is equal to 0. For each k. And limit n tending to infinity sigma k is equal to 0 to n, ank is equal to 1. This is row sums. Row sums is equal to 1. Second property is known as terms of any column tends to 0. First property is known as uniformly bounded summable rows. And this is the matrix analysis, matrix summability analysis. Our operator is Tn is equal to sigma k ank sk. K varies from 0 to n and this. For example, you prove that is Banach contraction principle, that is a complete metric space, a contraction mapping on a complete metric space have Unifish-Pine. In order to prove Banach contraction principle or Banach-Fishpine theorem, we form the iterated sequences. Like in a similar way, we form here iterated sequences. That is T0 is equal to A00 S0. T1 is equal to A10 S0 plus A11 S1. T2 is equal to A20 S0 plus A21 S1 plus A22 S2. And so on and so forth. Tn is equal to An0 S0 plus An1 S1 plus An2 S2 plus so on and so forth plus An Sn. If we write these equations in matrix form, then this will be left hand side, that is T0, T1, T2, T3, and so on and so forth, Tn and so on and so forth. This is the output signal sequence, output sequence of informations. And here right side, that is S0, S1, S2, S3, and so on so forth, Sn, and so on so forth. This is called as column operator, also column matrix. And middle matrix, that is T is equal to Nk, Toeplitz matrix. Toeplitz matrix, that is a first entry A00, A10, A11, third row A20, A21, A22, and so on so forth, AN0, AN1, AN2, and so on so forth, ANN. And NP mean, that is Narlund mean similarity, 1 upon Pn, sigma k is equal to 0 to n, Pn minus mu S nu. These are the various type of operators, Narlund operator. We can define it in the next slide in detail. This is Narlund filter. And how to get C1 from this filter? NP bar, Pk is equal to 1, then Pn is equal to n plus 1. And in NP bar, Pk is equal to 1 upon k plus 1 for every k greater than 0. Then capital Pn is equal to log n in NP bar summability. And in NP bar, Pk is equal to Ek alpha minus 1, then Pn is equal to En alpha. We get C1 summability. This is next operator, that is C0 operator. If for alpha greater than 0, Ank is equal to En minus k alpha minus 1, and upon En alpha, or 0 less or equal to k less or equal to n, and 0 for k greater than n, where En alpha is defined by gamma n plus alpha plus 1 upon gamma n plus 1 gamma alpha plus 1, which is equal to sigma k is equal to 0 to n Ek alpha minus 1. Then the linear mean Tn reduces to C0 mean of order alpha, that is C alpha, and the general term is denoted by sigma n alpha. The series sigma un is said to be C0 summable C alpha to S. The series sigma un is said to be C0 summable, that is C alpha summable to a finite number S if sigma n alpha is equal to En to the power minus En minus alpha, sigma k is equal to 0 to n En minus k alpha minus 1, Sk converges to S as I am tending to infinity. Let us consider this infinite series. This is oscillate finitely series, oscillate finitely. Because oscillate finitely, what are the oscillate finitely? Oscillate finitely sequence, let us study. A bounded sequence which does not converge, that is called oscillate finitely. And an unbounded sequence which does not diverge is called oscillate infinitely. So the series sigma minus 1 to the power n, that is 1 minus 1 plus 1 minus 1 plus 1 so on so forth, is C1 summable to a finite number 1 upon 2. Here S1 is equal to 1, S2 is equal to 1 minus 1, 0, S3 is equal to 1 minus 1 plus 1, that is 1, S4 is equal to 0, and so on so forth. For C1 summability, Tn is equal to S1 plus S2 plus 1 so forth plus Sn divided by n. Okay. Case first, if n is an even number, that is n is equal to 2m, then Tn is equal to S1 plus S2 plus 1 so forth plus S2m divided by 2m. That is equal to 1 plus 0 plus 1 plus 0 plus 1 so forth plus 1 plus 0 divided by 2m. That is m upon 2m, that is 1 upon 2. Because half are 1 and half are 0. So numerator sum is equal to m. There are 2m number of terms, half are 1 and half are zeros. Case second, if n is odd number, that is n is equal to 2m plus 1, 2m plus 1, then Tn is equal to S1 plus S2 plus 1 so forth plus S2m plus 1 upon divided by 2m plus 1. That is 1 plus 0 plus 1 plus 0 so on so forth plus 1, 0 plus 1 divided by 2m plus 1. That is equal to, there are 2m plus 1 number of terms in the numerator. Okay. And the numerator sum is equal to, what are the numerator sum here? 1 plus 0 plus 0 plus so on so forth plus 0 plus 1. Numerator sum will be equal to, anybody can tell what is the numerator sum? कोई बताएंगे? Anyone? Numerator sum is equal to m plus 1 because there are 2m plus 1 number of terms in the numerator. Up to 2m number of terms, that is m, last term is 1. So m plus 1 divided by 2m plus 1. It is improper fraction. Okay. You divide the numerator by denominator till the degree of numerator is less than degree of denominator. and letting m tending to infinity, then the sum equal to 1/2. So in both cases, if n is even and if n is odd, then sigma minus 1 to the power n is C1 summable to the finite number 1/2. Okay. Thus, the number 1/2 is assigned to the infinite series sigma minus 1 to the power n. Similarly, a number 1/4 is assigned to the series sigma minus 1 to the power n into n plus 1. Okay, of course it is C2 summable but not C1 summable. Of course it is C2 summable but not C1 summable. If any infinite series is C2 summable, then it is not guaranteed that it is also C1 summable. Null summability, NP summability. If nk is equal to Pn minus k upon capital Pn for 0 less or equal to k less or equal to n and 0 for k greater than n, where capital Pn is equal to summation of all little pk's, k varies from 0 to n, and p minus 1 is equal to 0 is equal to capital P minus 1, because if we apply Abel transformation, then such type of a term appears. So that in definition we say that they vanish for negative values of n. That is pk, k varies k for negative values of k. And then the linear mean Tn reduces to null mean npn denoted by nn, where Pn is any sequence of real or complex numbers. The series sigma un is said to be null summable, np summable to a finite number s if nn converges to s as tending to infinity. If nn converges to yes as tending to infinity. Okay. Example of non-regular summability methods. This example has been taken from paper of Professor Prem Chandra, published in Trigonometric Approximation of Functions in LP Norm. Title is Trigonometric Approximation of Functions in LP Norm, and published in Journal of Mathematical Analysis and Applications, 2002. Recently, in 2021, Professor Prem Chandra passed away, and this example has been taken from his paper, JAMA, 2002. ENFX is the degree of approximation, that is error in approximation. A general mean, that is linear mean, Norlund mean. 1/Pn sigma Pn minus m Sm fx. M varies from 0 to n. And Pn is equal to C to the power n, where C greater than 1 and n greater or equal to 0. We have already supposed this. And capital Pn is equal to little sum of all little pk's. And we know that P summability method is regular if and only if Pn minus k upon capital Pn is equal to 0 for each fixed k greater or equal to 0. After calculation, we have shown that this is not equal to 0. Okay. Let us come next, that is reach NP bar summability operator. Reach NP bar operator. If nk is equal to pk upon capital Pn for 0 less or equal to k less or equal to n, and nk is equal to 0 for k greater than n, where capital
Dr.
Pn is
Mishra,
equal
can
to
we? Hello.
Yes, Professor Sahu.
Yeah, please try to go for the conclusion. That is why the time is short.
Okay. These are the various type of operators, and there is very important tool, that is Fourier approximation also. We are speaking Fourier in a Fourier approximation, that is signal is integrable in the sense of Lebesgue, not Riemann. There is very much important theorem in Fourier approximation, that is known as correlation-Hunt theorem. That is the point-wise convergence of the partial sum of Fourier series is one of the hardest result in mathematical analysis. L correlation result. Property hold almost everywhere. And this is the difference, that is in Fourier approximation, signal is integrable in the sense of Lebesgue, because we can define the source things on smooth functions and then take the limits to extend our result to LP function. All this is impossible in the smaller space of Riemann integrable functions. And let us see, these are the examples of Fourier approximation. Signal processing. approximation theory, control theory, partial differential equations, and many other fields also. So how much time remaining?
Sir, we have shortage of time. Can you go for the conclusion? We are going to end.
Okay. 5 minutes or 2 minutes?
2 minutes.
Okay, yeah. Let us see, this is the model of our problem. That is the problem, that is T and Fx is equal to sigma k is equal to 0 to n, a n k s k fx, n varies from 0, 1, 2, 3, etc. Sn is the input sequence of information and Tn is the output sequence of information. Then T is equal to nk behaves like a digital filter. This is the filtering process, filter. And use of general matrix similarity method. This is the input sequence of information, and Tn is the output sequence of information, and this behaves like a digital filter here also. This and the trigonometric Fourier series has played a very significant role in the solution of various physical problems, and its applications are of vital importance, have been found in telecommunication engineering, digital filter, and the analysis stochastic problems. This is the Tn is equal to this mathematical model of the problem. This Sn is the input signal sequences, and Tn is desired output signal sequences. There are transmitter and receiver. Transmitter, that is echo plus noises. They reduce echo plus noises and gives the best approximation. Error in approximation is very less. That is, we get the best output result of our problem through this process. And this is the in, this is output, and delay, amplification, summation, etc. So these are the applications of this transformation, which we have discussed in the start. And I am very much thankful to you all, which have listened me in patience. And this is the branch of mathematics, that is approximation using positive linear operators, using summation type operator and summation integral type of operators, through which we can make the system as stable and convergence problem summable. Summation is finite. So this is the beauty of this branch, and it is applicable in every branch of mathematics. So I am very much thankful to the organizers of this prestigious symposium on this platform. So any queries, please ask. Thanking you very much for the same. Thank you, sir.
Questions, please. Any queries or suggestions? Okay, so if there is no questions, let us thank Professor Mishra for the nice talk, and thank you all the participants for attending the morning session with the nice invited talks. Thank you all. So over to Majid sir.
Thank you, sir. Thank you, Professor Vishnu Naran Mishra and Professor P.K. Sahu. And our next session will start sharp at 2, and the lecture will be delivered by Dr. Rakesh Kumar from Patiala University. A session will be chaired by Dr. Mubin Ahmed. So actually we are already half hour late. So we will be meeting at sharp 2, inshallah. Huh? So please join time. Thank you each and everyone. Thank you very much.
Thank you, Professor Majid.